From the sanitizer in your hand, to the fragrance in your perfume, to solvent in your lab reagent bottle, alcohol, phenol and ethers silently controls the acidic nature, the hydrogen bonding, the reaction pathway which JEE loves to twist in tricky questions. So master this one chapter in a single gunshot with me, and suddenly you will find the boiling point, the acidic nature, the reaction pathway, and even the naming reactions will fall suddenly into place in whole of your organic chemistry. So hello my dear JEE aspirants, and I am telling you one more thing for all those class 12 students. These notes I have made in such a way that you do not have to write these notes because you are having shortage of time. You can download all these notes. It will be definitely helpful for your class 12 boards also, and definitely for mains also, but for mains you need high impact practice questions. So where to find all of them for free? Just go to the link in the description section where you will be directed to the beautiful world of PW, which is also helping thousands of students like you to excel in their competitive journey. You can also follow us at PW J English WhatsApp channel to stay updated. So let us start this chapter. Yes, so starting with classification of alcohols. So alcohols, which is the functional group OH, if that functional group is connected to a carbon which is sp3 hybridized, as in which is forming 4 sigma bonds, then those alcohols are alkyl alcohols. It may be primary or 1 degree, secondary or 2 degree, tertiary or 3 degree. So these alkyl alcohols are further classified as primary, secondary and tertiary on the basis this functional group is connected to what carbon. If that carbon is connected to one set of alkyl group, it is a primary alcohol. If 2 set of alkyl group, it becomes a secondary alcohol, and if 3, then it becomes a tertiary alcohol. Now this is what are the general names. This is an ethyl alcohol. Ethyl alcohol because 2 carbons are in a straight chain, they are having OH, so it is also called normal alkyl group. So normal ethyl alcohol. What is iso? Iso is also a general name. What does it signify? You should have first carbon, second carbon and a methyl branch. This photo is known as iso picture. Now this iso general name is only attained when you have a methyl group at the second carbon, and because it's a general name, so you count the total number of carbons. How many are there? 3. So it becomes a isopropyl group. And to this isopropyl group, what functional group is added? OH, so it becomes a isopropyl alcohol. Similarly, the general name, this becomes a tertiary carbon. This is the simplest tertiary carbon. You cannot have a smaller tertiary carbon from this. So this is the smallest tertiary carbon, and it is formed by how many carbons in total? 4. So this becomes, the general name becomes tertiary butyl group. And to this group, if I added a functional group which is OH, so general name becomes tertiary butyl alcohol. Now one thing I want to mention to students at the beginning, for if you are reading this for boards, I'm starting from 0, so do not worry. I'm starting from 0. It will be definitely helpful for your boards also. But for all those students who are watching this in order to have a mindset that you should clear JEE mains, then one thing I'm telling you, organic always in January attempt also we have seen, if at all you are lucky, they just give you NCERT reactions which we'll be getting. So even if you are preparing till your board level, mains question of those level will be done. But some sessions have organic questions as a mixed packet where you need to know the common sense of organic chemistry. So for those good and moderate and difficult level of organic questions, you do not have to do some rocket science. Just in this PW JEE English channel only, always start organic from basic. So do it sequentially. Do first GOC1, then GOC2, then hydrocarbons, then alkyl halide, which is already there in the channel, and then come to this chapter. Sir, but I have very much less time. Then make a speed of 2x. And that 2x, with that 2x speed, if you watch, the time that you will be requiring to finish this is also reduced. But if at all you are not having time at all in here also, I'm starting from 0, so do not worry. Now this finishes the classification, the first classification, which is sp3 hybridized carbon bonded with OH. Sir, uh, sp3 hybridized carbon bonded with OH have some different classification also. Yes, they can also be uh, characterized as allylic alcohol. Now, what is an allylic group? The sp3 hybridized carbon next to a double bonded carbon. This yellow colored carbon is also generally termed as an allylic group, and to this allylic group I add alcohol, then this becomes a allylic alcohol. Obviously it can also become 1 degree, 2 degree or 3 degree. Right now it is a 1 degree alcohol. Why? Because OH is connected with this carbon, and this carbon is having how many alkyl group? For sure, 1. That alkyl group may be of any carbon nature. If it is having carbon chain over here also, it will become a 2 degree allylic alcohol, and in this way it becomes a 3 degree allylic alcohol. Now, one more example of allylic alcohol is this guy. Sir, but it is having benzene ring. Benzene ring is not directly connected with alcohol, the functional group. The functional group OH is still connected to an sp3 hybridized carbon, and that sp3 hybridized carbon is next to a double bonded carbon. So this is also an example of allylic alcohol, but it is also generally named as benzylic alcohol. So benzylic group is nothing but an example of allylic group. So this is benzylic alcohol, and this benzylic alcohol can also be 1 degree, 2 degree, 3 degree. Right now, if I have 2 hydrogens, so it will be a 1 degree benzylic alcohol. If this is R, then it becomes a 2 degree benzylic alcohol. If that is also an alkyl group, that it becomes a 3 degree allylic alcohol. Moving to the classification on the basis of carbon, on the basis of compounds containing sp2 hybridized carbon containing the OH. We have recently seen what? Sir, if I have a benzene ring, then this carbon is an sp2 hybridized carbon. If this carbon is directly connected to OH, this group, if double bonded carbon has a free valency, that group is generally termed as vinylic group, as in double bonded carbon having free valency. But in general, these vinylic alcohols are not stable. Why? Because oxygen is also electronegative, sp2 hybridized carbon is also electronegative. They will have a fight which increases the internal energy of the system, and the system cannot remain stable at room temperature. But because of stabilization of resonance to this pi electron cloud, this vinylic alcohol is stable, and therefore this aromatic compound is termed as phenol. We definitely know all the aromatic stable compounds containing the benzene ring, they are also characterized by their general name, and their general name are so famous that even the systematic name, that is IUPAC, also accept those general names. So this is known as phenol, your basic aromatic alcohol, but what it is a type of a vinylic alcohol. Now, moving to the next set of classification, third is on the basis of, like in alkylides we have seen, if number of OH functional group changes, then it can be a monohydric alcohol. If it is 2, then it can be a dihydric alcohol. If the functional group are 3, it can be a trihydric alcohol. It can be a polyhydric alcohol. Now, the basic examples, obviously we know this is ethyl alcohol. Now, what will be it, this IUPAC name of this dihydric alcohol? Sir, functional group is OH, so this will be main chain. This is 1, this is 2, so its IUPAC will be ethane 1,2 diol. But it is having a very famous general name also that you should learn. It is called ethylene glycol, or simply glycol. So if at the vicinity I have 3 carbons, and at each carbon I have OH, IUPAC will be propane 1,2,3 triol, but I have not written that name because that is the basic that we know. What is here important is the general name, and the general name for this guy is glycerol. So whatever are the important things, I am deliberately, I have already written them very properly so that you do not have to write it now. Download these notes and read them by heart. It will not be remembered in one day. You listen to this one shot. If required, listen to this again with a 2x speed the next day, and download these notes and keep on rotating these notes in the morning. I am telling you, in 3 to 4 days, just start reading them. these notes, read them aloud so that you can listen to your voice. In 3 days, I'm telling you, you will be remembering all the concept, all the naming reactions. Moving to, for your boards, I'm telling you. Now, moving to the next set of classification, dihydric aromatic alcohol. Sir, in monohydric, dihydric, trihydric, sir, aromatic alcohols can also be obviously. So if I have phenol, but if I have 2OH, so this becomes a dihydric. But now the general name will not be phenol, so it will be benzene 1,2 dihydroxy, benzene 1,2 diol, because OH is functional group, and for OH what suffix we use? All. But here also I am not interested with the IUPAC name. IUPAC we have already completed in GOC. Here I am interested in the general name. They are given in NCERT and very, very famous for JEE. So this orthoisomer is termed as catechol, this meta isomer is termed as resorcinol, and this para isomer is termed as quinol. And obviously the IUPAC name will be benzene 1,2, 1,3 and 1,4 diol. Hydroxy is a prefix of OH which is used only when a senior functional group is attached. There is OH is the only functional group over here, so we use its suffix which is all. So I've given you the IUPAC also, but here the important thing is the general name. Now, sir, if phenol is substituted with a methyl group, then it can be ortho meta para 1, 2, 1, 3, 1, 4. But this is also generally loved by JEE and it is termed as cresol. So ortho cresol will be 1, 2, para cresol will be 1, 4 and metacresol will be 1, 3. So this general name is known as, this substituted phenol is known as cresol. Now, sir, we have classified alcohols and phenols. What about ethers? Now, ethers are basically of two types. They may be symmetrical or simple. As in what is ether functional group? When oxygen, both the bonds are connected with alkyl groups, and if the nature of alkyl groups are same, as in both the alkyl groups are similar, it becomes a simple or a symmetrical ether like this one. So this will be generally named as dimethyl ether. This will be diethyl ether, and obviously if they are different, it will be a mixed or an unsymmetrical ether, when at one side you have different carbon chain, at other side you have different carbon chain. So general name of this unsymmetrical ether will be this is a methyl, this is a phenyl, this is a methyl. So MNOP, M comes first, so its name will be methyl phenyl ether. But because it is aromatic, so some general name may also be used. And yes, a general name is famous for this guy also. When benzene ring contain OCH3, it is generally termed as anisole. Now, let us name this unsymmetrical ether. Now, ether as a function, it is a functional group, but its nature is different. Different as in the reactivity of ether are relatively lesser than that of alcohols, but they are functional group. But because the reactivity is lesser as compared to alcohols, therefore in IUPAC naming also, the ether is always treated as a branch. It is never treated as a functional group so that its suffix is used. Always for this functional group, like for halogens are functional group, but for naming we just take them as a branch. So for naming, their prefixes are only defined. So for ether also in IUPAC, only their prefixes are defined, and their prefix is just the name alkoxy. So main chain will be these two carbon, and this will become a branch. This branch is having one carbon, ether as in methoxy. So its IUPAC name will be 1-methoxyethane. I hope we are clear with this. But what will be the general name? At ether, there is at one side it has having a methyl group starting with an M. On the other side, it has an ethyl group starting with an E. E comes first. So general name will be ethyl methyl ether. I hope we are clear with this, because again I'm telling you, IUPAC have separately discussed in GOC, although I'm discussing everything over here also. But for writing and practicing, you should obviously check the GOC-1 area of IUPAC and then continue over here if you're reading it for the very first time. For boards, this is more than sufficient. Moving to the IUPAC and isomerism. IUPAC and isomerism, as I'm saying, in GOC1 we have discussed in stretch. So let us combine and read them through questions. So the first question is ethanol and dimethyl ether. Sir, you already told us both are having functional group O. But when one O is connected with an H and one with a alkyl group, then I am called a alcohol. Having different chemical properties, and ether having alkyl group on both sides have different chemical properties. So because the nature of functional group is different, so what isomerism they will show? If they have same molecular formula but different nature of functional group, then it is definitely termed as a functional isomer. So our answer will be functional isomer. And remember, these are not just random questions. This was a question from JEE 2024. Yes, it was a match the column question, and it was one of the option among the 4 match the columns. But I have picked all those relevant things for you as per your JEE examination, as per your board's examination. So by this we are revising the common sense that alcohol and ether are what isomers of each other? They are functional isomers of each other. Now, the next question says, for this compound, you have to tell the number of stereoisomers. So stereoisomers are generally of 2 types. I'm just talking generally because precisely we have already discussed in GOC. So generally, revising again from 0. Generally, you should know stereoisomers are of 2 types. Geometrical isomers, they have same molecular formula, but because of restricted rotation, they have different orientation in 3-dimensional space. So cis-trans, when similar group, same side, so cis, opposite side, so trans. And optical isomers. What are optical isomers? They also have same molecular formula, but they have different nature of rotating, different nature and ability to rotate the plane of a polarized light. Somebody rotated clockwise, so it becomes dextrorotatory. Other becomes rotated anti-clockwise, so it becomes levorotatory. Sir, optical rotation can be identified by looking at the molecule? No. Optical activity can only be determined through experiments. So we have done those experiments and we have determined what? That every compound who is optically active contains a unsymmetrical center, achiral center. What is a asymmetrical center? And asymmetrical center is also, in English, it is also termed as chiral center, not achiral, chiral center. In nature, there are various examples of chiral center. One of the very famous example of chiral center is a sp3 hybridized carbon having 4 differently substituted bonds, the chiral carbon. And that is what you need to remember for JEE mains and for your board's examination. Although there are more asymmetric centers also, but for your JEE knowledge, for your till mains, you should only remember that who is the most famous asymmetric center? A chiral carbon. What is a chiral carbon? Like over here, if you look at this carbon, one bond is CH3, which is methyl group. One is OH, one is this bigger carbon chain, and one will be hydrogen, which makes this carbon a chiral carbon. So this can be dextrorotatory, this can also be levorotatory, but it is also having one more stereo center. What is it? An alkene. So because of this alkene, it will be having one hydrogen. This will also be having hydrogen. So hydrogen on same side, so cis, opposite side, so trans. So if you talk of stereoisomerism, it can show optical also, it can show geometrical also. So how to calculate number of isomers? This is 1, this is stereocenter 1, this is stereocenter 2. Because of this stereocenter, it can show dextro-levo, so 2 options. Because of this, it can also show, it can be cis also, it can be trans also, so 2 options. So this becomes a question of probability permutation combination for you. So 2 into 2, as in 2 raised to the power n, as in 2 raised to the power number of stereo centers. So what will be your answer? Your answer will be beautifully 4. So how many stereoisomers you have? 4, because you have 2 stereo center, optical also, geometrical also. This is also a JEE mains question. Moving to the revising isomerisms also from the scratch, practicing questions also, relevant questions. Now, the next question says the number of optically active compound. This is also a 2024 question. So out of these, we have to pick the number of optically active compounds. Now, Sir, this is having a chiral carbon, agreed. Sir, this is also having a chiral carbon, agreed. But if you have a chiral carbon, overall molecule should also not have any element of symmetry, because actually a optical stereo center is an asymmetrical center. You should not have any element of symmetry. And this guy over here, we can clearly see, let me mark it for you. This guy over here will have a plane of symmetry. If I cut this molecule along this plane, it will be divided into two halves. So because it is having a plane of symmetry, which is an element of symmetry, although it contains chiral carbon, but overall activity of the compound will be 0. So what type, this is a Fisher projection of showing a chiral carbon, which we have done in GOC in detail, but I am discussing everything here also with example. So this is a optically inactive compound, and such forms, such optical inactive forms are called mesoforms, because it individually it contains chiral carbon. But let's say this carbon will rotate the light to clockwise direction, this will rotate 20 clockwise direction. Ultimately the light will not move, so ultimately this compound is optically inactive, and therefore whenever you have an element of symmetry, overall compound becomes optically inactive. Similarly, if we check this carbon, so here also this is also chiral, this is also chiral, and this is also chiral, and it is not giving you the exact stereochemistry of the molecule. So the single bond can freely rotate. So are you sure maybe this will also have a plane of symmetry? Yes, there may be a case that these OH are on same sides, and it can also be broken into two similar halves like that one. So in nature, in three-dimensional space, it may also form a mesoform. Yes, it may also form an optically active form, but it may form a mesoform as well. And the question is saying number of optically active compounds. So are you sure? Because here the question is giving you a bond line formula, so it can have any orientation in space. So if that orientation is like this, where if these OH are on similar sides, then this will act as a plane of symmetry again. So this may become optically inactive also. So can you count it in your question as number of optically active? You are not sure that it will be optically. It may or it may not be. So to be safe, we will not take this as optically active compound because it has a plane of symmetry. What about this one? So this is a simple case. There is no chiral carbon, so no optically inactive. Yes, this carbon is chiral, and because of chiral it will have two isomers, dextro and levo, so this will be optically active. What about this one? No chiral carbon. What about this one? This guy has two methyl groups, so two methyl group, all the four bonds should be different, so this is also not having any chiral carbon, so your answer will be beautifully 1. So these all are JEE questions through which we have revised isomerisms also. And moving to okay, I have one more question for you. Now the next question says, okay, let us read it. The number of chiral alcohols with molecular formula C4H10O. Now just look at the degree of unsaturation. In GOC also I've told you, I'm telling you again, because again I'm telling you I'm starting from 0, so do not worry. Now sir said if there are 4 carbons, then how many hydrogen it should have? 2n plus 2, so 4 to 8 plus 2 is 10. Sir, it is having 10, so the degree of unsaturation is 0. It is having no degree of unsaturation. No, it should not have any double bond. So let us make the options. So for 4 carbon, what will be the first thing that you will think? Sir, make them in a straight way. Now you have to substitute with oxygen. So what this oxygen can be ether also, but the question is also telling you that you have to only draw the alcohols and then say what are the number of chiral alcohols as an optically active alcohols you have. So let us decorate it with functional group OH. Now if I want to decorate this, so OH can come here also and OH can come here also. So I'll be having one option is this. I'm sorry, this is 1, not plus. So first is this isomer and second is this isomer. So why you're not placing over here? Because if I place over here, this will be 1, 2. So what will be its IUPAC name? This is butane 2 all. This is butane 1 all. Sir, can we have different yes, you can think of 3 carbon chain, but what about because it is having 4 carbon, so 4th carbon will be coming over here. Now, what are the possibilities of decorating this carbon chain with OH? I guess you'll have 2 possibilities, because this. You place OH anywhere, you will get the same name. What will be the name? Name will be 2-methyl propane 1 all. So this becomes your 3rd structure, and if this OH is substituted in this carbon, this becomes your 4th structure. Name will be 2-methyl propane 2 all. Now these are the 4 structural possibilities, no other structural possibilities. Now let us work on the chiral carbons. Every carbon, if it is having, let's say, 2 hydrogens, sir, all the 4 bonds should be different. So this is CH2. So obviously this is not chiral. I look at carbon, when I'm searching for chiral carbon, I do this. I see that if it is having 2 hydrogen, then it cannot be chiral. So obviously this is having no chiral carbon. What about this guy? Yes, sir, this carbon, 1 methyl group, 1 this ethyl group, 1 OH and 1 H. So this will be chiral. So this is one of the, so number of chiral, this is one of the option. Now let us search for the other one. No, this is not also not having any chiral carbon. What about this one? No, this is also not having. So answer for this question will be beautifully, answer for this question will be beautifully 1. Let me check it for you. Let me unlock it. Yeah, answer is 1. Now I've given answers also, so when you'll download this sheet, you will get those answers also. So why you have written that over here? My DTP just typed, and I thought that it was good also, because while practicing you cannot see answer, and after doing you can always check. So moving to the next question. Now coming to the next topic, which is structures of functional group. Now sir, we already know through VSEPR theory, but I'm telling you, I'm discussing everything. So what is VSEPR theory for this functional group oxygen? If I am an oxygen, then that oxygen is having 2 bond pair and having 2 lone pair. So oxygen having 2 bond pair, as in 2 sigma bonds. So bond pair will be 2, lone pair will be 2. Steric number, which is nothing but sum of bond pair plus lone pair, will be 4. So hybridization will be sp3. So hybridization of oxygen will be sp3, and shape with respect to oxygen will be bent, because it is having just 2 bonds. What about this angle? This theta, because of the presence of lone pair, we know through VSEPR theory, lone pair repulsion is higher. So lone pair will be more far apart from each other, and bond pair will come close. So if I have 4 species, 4 combining atoms, then shape is tetrahedral, and angle becomes, this theta becomes 109 degree 28 minute. But because I'm having 2 lone pairs, so they will be having more repulsion. So this angle theta, I do not know what it will be, but through the common sense that lone pair repulsion is higher, I can definitely say that it will be lesser than the tetrahedral angle, which is 109 degree 28 minute, because lone pair will be repelling. So these bonds will be coming closer. So theta will be lesser than the tetrahedral angle, which is 109 degree 28 minute. When we have gone to Mother Nature, this is the actual experimental data that I'm giving you. You do not learn the data, but learn the trend. What's the trend? Can you see that this is the simplest alcohol, methyl alcohol? In this methyl alcohol, what is the bond angle, sir? It is 108.9 degree. Don't learn the angle, but learn the trend. Is it less than 109 degree tetrahedral angle? Yes. What about phenol, sir? This angle over here, yes sir, it is also less than 1 tetrahedral angle. So that VSEPR theory is validated for alcohols and phenols, sir. But if you compare alcohol and phenol, you can clearly see that is 108.9 and this is 109. But sir, you said do not learn the data, but I said learn the trend. So which angle is higher? This is higher. Why? Because lone pair configuration is same, but here this is a methyl group, the bond pair getting repulsion from hydrogen. So whatever repulsion these bond pair will have, if that methyl is replaced by a bulky phenyl group, don't you have that feeling? Methyl is relatively small, so repulsion between methyl and H and repulsion between phenyl and H, phenyl will be repelling more, so slightly the bond angle will be increasing because of the bulkiness of this phenyl group. So slightly, not to a large extent, but slightly this angle is larger. That's why over there it is 108.9, but over here it is 109. A very famous and important point to not learn the data but learn the common sense. And because we have separately concentrated and focused on the repulsion between bond pair, then in ether we can obviously think that when this methyl has become phenyl, there has been an increase in repulsion between the combining atoms. So when for ether, if I have those bulky groups both the sides, because hydrogen is very small first period element, if I have alkyl groups on both the sides, then won't those alkyl groups will repel? They will definitely repel, because those alkyl groups are tetrahedral in themselves. So because of increase in the, so here the repulsion among bulky alkyl groups dominates. Why I'm writing dominates? Because as per VSEPR theory, it should be less than 109 degree 28 minute. I'm saying the repulsion between alkyl groups has dominated to a larger extent. Why? Because we have to learn not the value but the trend, that this angle for simplest ether also, do you have ether smaller than dimethyl ether? No. So for dimethyl ether only, if we go to mother nature, we have seen this angle is 111.7. that means this is larger than tetrahedral angle. So if I am larger than tetrahedral angle, that means I have repelled myself sufficiently large enough to overcome the repulsion between lone pair. Therefore, I'm saying for ethers, for all ethers, repulsion among alkyl group dominates, because as these alkyl group becomes larger, becomes contain more number of carbon, repulsion is definitely going to increase only. It is not going to decrease. So for ether, that VSEPR logic is not applicable, because this repulsion between alkyl group dominates. So this you have to remember. Now, one more thing. If you compare the C bond O bond length, I am not saying to learn the value. If you compare this bond length of C bond O is 142. And you should know for chemical reactions also, C, carbon and oxygen are both second period elements, which are very small, extremely small. So breaking C bond O is not easy. It is a tough task. Therefore, whenever we will see reactions also, breaking C bond O is very difficult, because it is a very strong bond, because the combining atomic orbitals are similar energized, and when similar energized orbitals make bond, they form a very strong covalent bonds. So what about the bond length? Do not learn the data, but learn the trend. This is 142 picometer. Okay, sir. In case of phenol, the bond length is even reduced. That means the bond has even gone stronger. Why, sir? This is also C, that is also this is also C, this is also O, that is also O. Obviously, if you know GOC, you know this through the phenomena of resonance. Sir, but you said you will be discussing from zero. I am discussing from zero. So before discussing this 2020 question of JEE mains, let me revise that GOC for you. Now, sir, what is resonance? Sir, whenever you have a group which is having lone pair and no empty orbital, so such groups are plus R group. What is a plus R group? They push their electron density to the conjugate system. What is the conjugate system over here? The benzene ring. So pi sigma lone pair, those lone pair will be pushed inside. So what will be the first resonating structure? You will be getting lone pair at the ortho position. This is again a conjugate system, pi sigma bond minus. So that minus will be coming to para position. It will again be going to ortho position, and then you will be getting the neutral structure back. So with these 5 resonating structures, you can see in these 3 resonating structure, this bond order is not 1, bond order is 2. So as bond order increases, bond length decreases and bond becomes stronger. So this is the resonance effect, and because of this resonance effect, obviously this C bond O has become stronger, like we have discussed in case of alkyl and aryl lights also. So normal C bond O of alcohol can be broken, but normal C bond O of phenol cannot be broken because bond length is less and hence it is stable. So in this question we have to arrange, this was a JEE mains question of 2020, it was saying to arrange the C bond O, the C bond O bond length in these. Sir, we definitely know that for a aliphatic alcohol there will be no case of resonance, so it will be a simple C bond O. For what? For alkyl alcohol, because there will be no sense of bond order increment, there will be no partial double bond character, so bond length will be largest for case of alkyl substituted alcohols. But for aromatic alcohols, we know because of resonance bond length will decrease, so phenol will have a smaller bond length of C bond O and methanol will have a larger. That is clear. But now I also have an option of para ethoxyphenol. That means I have a substituted phenol. So how will we compare this? Again, through the common sense. I am not denying to the fact that these lone pair will be in resonance. They will be in resonance. But they are not the only functional group that is attached. You will also give, I'm not denying to the fact, but you will be giving to a lesser extent, because now this OR can also act as a plus R group, because here also I have conjugate system, single bonded with an atom which is having lone pair, and lone pair is not having any, this oxygen is not having any empty orbital. So this is also a plus R group, which will also donate its electron through resonance, reaching at ortho and para position. So when this OR is giving electron, then that OH cannot give its electron to the ring, so this bond length, this bond order will remain 1. I am not saying that it will never do plus R. It will do plus R. It will also attain partial double bond character, but it will attain a partial double bond character to a lesser extent, because in case of phenol only this guy was giving, so it will be permanently delocalizing its electron. But this guy can only delocalize its electron when this OR is not delocalizing. So it will also have a fair chance of giving its electron to benzene ring. It will also have a fair chance. So when the chance will be shared, so the partial double bond character that will be attained by this C bond O will also be getting shared. So it will be having lesser resonance as compared to phenol. So here the bond order has been increased to more number of times, so this bond length will be lesser and this bond length of C bond O will be relatively larger. A very beautiful common sense, and therefore your answer will be option D, and I guess I have already given you the answer also, option D. I hope we are clear with this. A very beautiful and a logical question as far as GOC is concerned. So I hope we are clear till this. Moving to, okay, this we have done. Now moving to the preparation of alcohols. So alkenes can be used to prepare alcohol, and alkene producing alcohol is very much loved by JEE, because alkene is used and can be used to form alcohol by 3 different processes. The first process is by acid catalyzed hydration, as in you put water, but water is not an electrolyte too. So in order to initiate the reaction, we add few drops of concentrated acid, let's say H2SO4 or phosphoric acid. Now this is the reagent, and it does what? It does Markovnikov addition of water. There is occurrence of rearrangement, because we have seen in alkyl halides also, I will discuss here also in detail that what does Markovnikov addition mechanism is. It is electrophilic. What is electron loving species? The H plus that we have added as a catalyst. So that H plus attacks the electron cloud of alkene, a carbocation is formed, and what carbocation is will be formed, that will be more stable. And whenever a carbocation is formed, it is always the slowest step. So first, ring expansion. If the carbon plus is just beside a cyclic ring, then ring has Bayer strain. So 3 bonds to become 4 membered, 4 bonds to become 5 membered, 5 bonds to become 6 membered. And 6 membered ring, experimentally we know, is free from any type of angle strain. So ring expansion can take place, because carbocation, whenever it is formed, it is always the slowest step. Next, after ring expansion, we will again next check for rearrangement with that, if carbon is getting more stabilization in the adjacent position. So rearrangement can also take place. So all these things happens to an alkene when it is subjected to acid catalyzed hydration. And the last thing is, because a carbocation is a trigonal planar species, so the after the formation and stabilization of carbocation, the plus loving species, that is the OH, the electron of oxygen, can attack from upside also and from downside also. Therefore, stereochemistry of the product, it is, this reaction is non-stereo specific in nature. Whenever we say specific, we have done in GOC also. That means this acid catalyzed hydration is not reactant choosy. It can react with any of the reactant, and the stereochemistry is of the reactant is not as such taken into consideration when it undergoes acid catalyzed hydration. But sir, this you are giving lot of detail. For mains, what you should know, that it is Markovnikov addition, so stability of carbocation and rearrangement can take place, and the reagent is H2 in presence of water. Now, you can also do Markovnikov addition by the second process, which is mercuration demercuration. The reagent, first, in order to do mercuration, you add mercuric diacetate HgOAc in presence of water or THF. THF is a solvent called tetrahydrofuran. In mains question, you can only see HgOAc or HgOAc plus water also. Even if THF is not mentioned, do not bother, because I mean, the mains and sometimes even advanced, they want you to just know the things. Even if every detail of the reagent is not mentioned, you should know them by yourself. So this does mercuration, and after that reduction does demercuration, and demercuration is subjected by reagent NaBH4 in basic medium. So this is the reagent for mercuration demercuration. What does it do? It also do Markovnikov addition of water, sir. So what is the difference? Actually, over here no carbocation is formed. How do we know this? How do we know this? That we have to learn experimentally, because experimentally we have seen that in such reactions no rearrangement take place, and if at all carbocation would have formed, then rearrangement can occur. But when you have to do Markovnikov addition without any rearrangement, then we do mercuration demercuration. And one thing for advance, that this you can leave for mains also. What type of addition it is? It is an anti-addition, as in H and OH are added to alkene from the opposite side. Last is hydroboration oxidation. What is the reagent? B2H6. Now BH3 is a Lewis acid, therefore BH3 in nature exists as B2H6. So B2H6 is used in presence of organic solvent, which is again THF. Now once this B2H6 is introduced to an alkene, the boron gets added, and after that, how it is removed? It is further treated with H2O2, hydrogen peroxide in basic medium, and ultimately what happens? Water is added, as in H and OH is added. But how? It is added via anti-Markovnikov addition. What is Markovnikov? Negative part of attacking species, as in negative part of water is OH, is added to that double bonded carbon which is having lesser number of hydrogen. This is Markovnikov. This takes place in these two conditions, and the opposite takes place in case of hydroboration oxidation. Now Again, a thing for advanced you can leave for mains. What type of addition it is? Here H and OH are added from the same side, so this becomes a syn addition. And obviously here also no carbocation is formed, so you get an anti-Markovnikov product without any rearrangement, sir. But whether this is more than sufficient, but in order to give you the detail, let us do some actual questions. So coming to the first is acidic hydration. So suppose I have this alkene. Now I know, let us revise that mechanism. First of all, this pi electron cloud will be attacked by the this H plus. So this becomes a, this H plus is an electrophile. So this is electrophilic addition. And after that, what will be formed? Sir, carbocation. So carbocation over here, sir, over here, if this carbon gets the carbocation, it will be a 1 degree carbocation. And if this carbons get a carbocation, it will be a 2 degree carbocation, because 2 degree carbocation will be more stable. So this hydrogen will be added to this carbon. So what product we'll be getting? These 3 methyl groups will be as it is. Then I have this CH which will be getting the carbocation. This double bond becomes single bond. This is CH2, and the extra hydrogen is added to this carbon. Now, because relatively it is a stable carbocation, so what we will say, it is a Markovnikov addition. But in alkyl halides also, in hydrocarbons also, I have told you what, do not learn Markovnikov as the negative part goes to that double bonded carbon. Do by basic. What is the basic? Form the stable carbocation. Check whether it can further stabilize or stabilize itself or not. If there would have been a ring like over here, first we'll do ring expansion. After that, do rearrangement. So there is no ring, but rearrangement can take place. So if this goes to this carbon, it will gain any profit? No, because this is 2 degree. Here it will become 1 degree. But if this carbocation is coming to this carbon, sir, it will have more inductive stabilization. So how it will go? This carbon is not having any hydrogen, so carbocation stability is top priority. So what we'll do is, we will even ask the methyl group to take this electron and migrate to this carbon. Thereby this positivity will be attained by this green colored carbon. So let us draw this now. So ultimately, what is taking place? Methyl shifting. Why? Because we feel that carbocation degree is increasing. So if it is increasing, we'll do it. So this is 1 methyl. This is 2nd methyl. The 3rd methyl has been migrated, and this carbon, therefore, because 1 electron of the methyl it has taken, so it attains a positive charge. This is the CH. It has recently been given the methyl group, this one. Then there is CH3. So this carbocation now has become a 3 degree carbocation, which was initially a 2 degree carbocation. And now what will be happening? Now I guess it is quite easy for you. Now water with its lone pair will attack this carbon, and it will take and snatch electron from hydrogen. So we will get an alcohol. So what will be alcohol? So this is one group. This is 2nd methyl group. Let me draw those methyl group now. This is this carbon, has just now been introduced by the OH from water. Then I have this CH connected to CH3 and having a methyl group. Now let us name this. So because this is functional group, so this becomes 1st carbon, 2nd carbon, 3rd carbon, 4th carbon. As in 2nd and 3rd carbon are having methyl branch, so name is 2,3 dimethyl butane 2-ol. Definitely through mechanism we have studied what will be the product of Markovnikov addition. Do not do Markovnikov addition. I mean, in very easy questions it will help, but in good questions you have to do by the basics of reaction mechanism, which we have done. So let us do that again for this group. Dilute H2SO4 is also water in and small amount of acid. So this is also giving you a lot of electrophile, which is H plus. The pi cloud of alkene will be attacking. This carbocation is not stable, that is more stable. So what will be the first step? This CH2 will be getting this extra hydrogen and will be becoming CH3, and the positivity will be coming to that carbon because it is relatively more stable. That is 1 degree, this is 2 degree. But now first what offer you give to carbocation for ring expansion? Because this carbocation is just next to the ring, so yes, ring will try to expand, this bond will try to get opened up so that a 5-membered ring can be formed, and ultimately who will be losing the electron? This carbon will be losing this electron and it will be going to that carbon, so the positivity will be coming to this carbon, and this process is known as ring expansion. I hope we are clear till this. Now let us draw this picture. These are the 4 initial carbons, but the ring has just, okay, this bond has been, we are breaking this bond, so let me not draw this. This bond is intact, we have just now broken this bond, and this bond is getting formed with this carbon, which was CH plus. So this CH has recently got the electron of this carbon, so this guy will be getting the positivity and it is still bonded with it, and a methyl group is attached. So this becomes a 5-membered ring. But sir, this is not a beautiful looking 5-membered ring, so let us draw that 5-membered ring beautifully. This is how we draw a cyclopentane. The one carbon is having a positive charge, whatever it may be, and the next carbon to that carbon is having a, let's say this is the next carbon, is having the methyl group. Now after ring expansion, sir, still it can rearrange. Why? Because now although the ring has become a 5-membered ring, but this is a 2 degree carbocation. At adjacent position it will again be 2 degree, but over here it can become 3 degree. So we'll think of first ring expansion, then rearrangement. So because it is having a hydrogen, so this hydrogen will be going to that carbon, positivity will be coming to this, so this hydride shifting will stabilize this carbocation to a larger extent, and therefore this will be happening. This is CH3 and I'll be getting a positivity over here. Now what will be attacking now, sir? Again the water molecule. So I hope this is quite easy now. This H2O will be attacking, taking electron from the hydrogen, so H plus from the catalyst that was initially taken now have been given back, and I will get a OH over here. So if I get a OH over here, the product will be looking somewhat like this is a CHOH and this is a CH3. So this is 1, 2, 3, 4, 5-member ring having methyl at the first carbon. So 1 methyl cyclopentane, 1 all. So these are the products and the examples in order to understand acidic hydration of alkenes. Now second is mercuration and demercuration. So first we'll add mercury. Now I'm telling you one thing, if you do not know the mechanism of mercuration demercuration as per JEE mains, you can skip. So therefore I have written this for you. For good questions you should know this, but if it is more to you, the mechanism you can skip, but still giving a brief. So this is HgOAc as in mercuric diacetate. This is the CH3CO group. The mercury, because it is a metal, will lose electron, and this CH3 COO minus will be leaving the mercury, will forming the anion, giving a positive charge on the metal. Now the plus and minus will attract each other. This is a basic reaction mechanism. So alkene, because of pi cloud, is electron rich. So now this will be acting as electrophile, and this mercury when gets attacked to this alkene just like H plus, but here through experiment we know that because there is no case of rearrangement, therefore we will not form carbocation. So sir, what we will form? We will form a mercury bridged carbocation, as in definitely this plus is attracting this minus. So this alkene, I'm taking this methyl group, this is the alkene, and this pi cloud is getting attached to the mercury, forming a cyclic bridged mercury compound. No carbocation, mind you. Now because there is no carbocation, so no rearrangement will take place. And now, what about the next step, sir? Now, after the over there, also after carbocation formation, what you do? You get the water attack the lone pair of the lone pair of electrons on oxygen attacks the positivity. But sir, there is no positivity, but there will be partial positivity. So do not think of a complete positive, because no rearrangement takes place. But you tell me, the partial delta positivity, if coming over here, it will be 2 degree delta positive, it will be 1 degree delta positive. So partial delta positivity is stable where, sir? Over here. So here the lone pair of electron of oxygen will attack. Again, hydrogen will be removed in form of H plus, so OH will be getting added to this side. But as soon as OH from water is getting added, because this carbon will be receiving electrons, so this extra electron will be moving to mercury, and we will be getting this product as step 1 product, intermediate product after mercuration, because now this alkene has been mercurated. And what about demercuration? We'll do reduction. Reduction is done using NaBH4 in basic medium. So it will reduce. This will be removed in form of acetic acid. This will be removed in form of mercury, and reduction is addition of hydrogen. And this guy will also be getting hydrogen. So hydrogen coming this side and OH coming this side. So mercuration, demercuration will always be an addition of water. Addition of water via what? Partial positivity of carbocation is stable, where number of hydrogen will be less. So this is again a Markovnikov addition without any rearrangement, and this addition is an anti-addition. The H and OH in alkene are added on the trans orientation. So this becomes an anti-addition. Sir, what about the anti-Markovnikov addition? Now, mercuration demercuration mechanism is not there in NCERT, but mains love it. That's why I've given that separately to you. This is there. The third step is hydroboration oxidation, and it is there in NCERT also. So what about hydroboration oxidation? For basic, you should know only this. This is anti-Markovnikov addition of water. But mechanism also you should know, because NCERT also discusses that mechanism, which is not very difficult also. Now, because we already know BH3 in nature exists as B2H6 as a dimer in order to satisfy the Lewis acidic nature. But once the diborane is reacted with an alkene, now after seeing the electron richness, the pi cloud of alkene BH3, B2H6, the two BH3 molecules will separate, because now they are having excess of electron cloud of alkene. So B2H6 will be dissociated, and you will be forming, they will be giving you BH3 molecules. Now they are acidic because this boron is still having this empty orbital, and because of the presence of this empty orbital, it acts as a Lewis acid. So boron being electron deficient, alkene being electron rich, so minus plus will attract each other. So now this is behaving as an electrophile, electron loving species. Now they will be attracted to each other. Now because along the period size decreases, so size of boron is actually large. So a fatter atom will be getting attached to what carbon? Because I am fat, I will require more space. I will require less repulsion. So this boron will be added to that double bonded carbon, which is least hindered. So if I have this unsymmetrical alkene, because this is a methyl group, therefore the bulkiness of this methyl group will repel the even bigger boron in form of BH3. So this boron being a Lewis acid will be attracted by the pi cloud, but it will be getting attached to that carbon which is least hindered. Therefore, among this carbon and this carbon, it will be getting attached to this carbon because relatively it is least hindered. Now, how the attachment take place? BH3, this B bond H is just getting broken. This C bond H is just getting formed. this pi bond is just getting broken and this new C bond B is just getting formed. So actually a intermediate is formed which will help you to understand this, that the manner in which boron is added to the alkene, in the similar direction, in the similar region, in the similar stereochemical composition, both hydrogen and boron are adding along the same side. So this becomes a syn addition which you can leave for advanced question. For mains you should not know this, but at least mechanism is there in NCERT. So obviously when BH3 has attacked one alkene, BH2 got attached to the first carbon because it is least hindered, and the hydrogen of this BH3, so it is the BH3 has been broken as BH2 and H. So H has gone to this carbon and BH2 has gone to the less hindered carbon, giving rise to an intermediate. But again, sir, again now this boron has again become a Lewis acid, although now it is having a plus I effect from the alkyl group, but still ultimately the octet of boron is still not complete. So but because of plus I, boron must be feeling happy, so it will try to do the thing that has made boron happy. If something makes you happy, you will try to do that thing as many number of times as you can. So because boron is still Lewis acid, so it will again try to do the same thing. How many number of times? The number of hydrogens it is having. So again this BH2 will be getting added to one more alkene, and again to one more alkene, so two alkenes because it is having two hydrogens. So that similar thing will be happening 3 times, and I will be getting a trialkyl borane intermediate. So this is the intermediate product of first step, which is action of B2H6 in presence of THF will alkene will ultimately result in the formation of trialkyl borane, with boron getting attached to that carbon which is least hindered, and the other carbon will be getting the hydrogen of BH3. So 3 hydrogens of BH3 has gone to 3 alkenes and resulting into the formation of this intermediate product. Now what is the reagent of hydroboration oxidation? So hydroboration has been done. Now oxidation. So after that, for oxidation, it is further treated with H2O2 in basic medium. Now what it will do? It will add excess of OH. So when boron will also get OH and these carbon will also get OH. So boron will get how many OH? 3. So it becomes H3BO3, which is your orthoboric acid. But it is a byproduct for us because we are studying organic chemistry. And this guy will be getting OH. Now because boron and hydrogen has been added from the same side, so H and OH will also be added from the same side. So this becomes a syn addition. But now look at the product. Negative part of water is OH is getting attached to what carbon which is having more number of hydrogens. So this becomes an anti-Markovnikov addition of water. But over here also, because no carbocation is formed, so here also no rearrangement will take place. So the first slide that I have given you is more than sufficient. Why I'm saying it is more than sufficient? Because we'll see that through the questions. But before coming to the question, let us finish the other preparation of alcohols. So the first method of preparation of alcohol is from alkene. From alkene you can prepare alcohol by 3 methods already seen. The second, the capital B, the second method of preparation of alcohol is from carbonyl compounds. Carbonyl compounds are having carbonyl group like aldehydes and ketones. Aldehyde is a compound when the carbonyl compound has at least one hydrogen. The alkyl group can be anything. It can be alkyl group and can be aromatic benzene. So even alkyl or aryl halide both, even alkyl or aryl group, not halide, if alkyl or aryl group, any of the group is connected to a carbonyl carbon having hydrogen, this becomes an aliphatic or an aromatic aldehyde. So you may be any aldehyde. If you are treated with a reducing agent, the reducing agent adds hydrogen, so add hydrogen. So if I add hydrogen to this guy also and this guy also, pi bonds break and you will get a alcohol. So that alcohol will definitely be a 1 degree alcohol. Now why I have it written generally? So you will feel, sir, it will always be a 1 degree alcohol. No. if let's say this is also hydrogen, then only for formaldehyde I'm writing this, because formaldehyde will form an alcohol which will be a methyl alcohol. Methyl alcohol is not even 1 degree. So just because of the formaldehyde option, I'm saying that aldehydes generally produce 1 degree alcohol, because formaldehyde produces just methanol, which is not even 1 degree. For methanol, no degree is defined. Now, but ketone is definitely having a carbon group on both the sides. So when it is subjected to reduction, this pi bond will definitely break. Hydrogen will be added. So it will always give you an alcohol. And what degree of alcohol? It will always give you a 2 degree alcohol. Very simple, have a very loved reaction by JEE mains. Now, even your boards. Now, what are the reducing agent which can do this? There are a list of reagent which can you do this, but for your mains and boards syllabus, you should learn these 3 by heart because they are very famous. First is catalytic hydrogenation, as in hydrogen in presence of a solid metal like nickel, platinum, palladium. Then you have a very strong and expensive reducing agent, which is lithium aluminum hydride. And the last is sodium borohydride, which is NaBH4. Or for NaBH4, it is very famous. You should always remember. NaBH4 is a reducing agent, but it specifically reduces only aldehydes and ketones. Always remember this. This NaBH4 is a very selective reducing agent. It only reduces aldehydes and ketones, although they can also, but they are strong reducing agent. They reduces other functional group as well. Sodium borohydride only reduces aldehydes and ketones. So these are the 3 reducing agent. Now, sir, but carbonyl group is also present in carboxylic acids. So when I have a carboxylic acid, what is the strongest reducing agent? Sir, you have already told us it is lithium aluminum hydride, but with acid, after reaction with LiLH4, LiLH4 is generally used with organic solvent like ether. So after that, we do hydrolysis. So the experimental fact for using LiAlH4 is, first, you do reduction with LiAlH4. Even if you are an acid, because I'm the strongest, I'm a very, very strong oxidizing agent. So I will add hydrogen till you reach to a level of 1 degree alcohol. So carboxylic acid always produces 1 degree alcohol, but industrially, because LiAlH4 is very strong, it can do this action very specifically. These hydrogens are supplied by this strong reducing agent, but it is very expensive. So rather, the product that we get is not even sold in such a high price, which is the price for this expensive LiAlH4. So what alternate we do is, we'll discuss this in the later slides, the mechanism also, but this reaction you know from class 10th, that is esterification. So acid reacts with alcohol in acidic medium and will form ester. This process is termed as esterification. So industrially, this becomes an economical alternate to do what? To convert acid to alcohol. So this carboxylic acid, when treated with any alcohol in acidic medium, first it forms an ester. Now, we'll learn this, we'll understand this with the mechanism of esterification as well, but I'm telling you right now also, because you should remember this is very important. While esterification, hydrogen of alcohol is removed and OH of acid is removed. So that's why I have specifically mentioned these brackets for you, so that these notes will be the ultimate notes from which you'll be revising everything. So HOH gone, and this OR dash will be getting added to the carbonyl carbon, and it will be giving rise to an ester. Now, ester are easily and economically reduced. Why I'm saying easily and economically? Because the basic reducing agent which you know from class 10th, which is catalytic hydrogenation. So this hydrogen in presence of nickel with small amount of heat can even reduce this. So after reduction, this oxygen will also get hydrogen. So you will get this side, the left side will be getting 1 degree alcohol that we were getting in the by using this expensive reagent, and the alcohol that we have invested initially is reproduced. So industrially, whatever alcohol you have used, it is again regenerated along with the production of the desired alcohol that you were producing using a expensive reducing agent. So this becomes a very economical option. Even NCERT discusses about it. Moving to the last preparation of alcohol. So first is from alkene. Second is by reduction of carbonyl compounds, and third becomes from Grignard reagent. Actually, from Grignard reagent also it is a common sense of carbonyl compounds only. Why? Because Grignard reagent, when introduced to any aldehyde or ketone, I'm again telling you, Grignard reagent. Now Grignard reagent having alkyl group or even aryl group, because this metal is highly electropositive. So with comparison to this metal, any R or even aryl group, so even benzene carbon can be given this minus because this is a metal. So this minus will be attracted by what? Plus. So this becomes a plus loving species as a nucleophile, and this nucleophile will be getting added to the carbonyl carbon, giving rise to a nucleophilic addition reaction. So this nucleophile attacks and gets attached to the carbonyl carbon, shifting the pi cloud to oxygen. So this O minus ionically gets bonded with magnesium plus, but this becomes an intermediate because Grignard reagent can only function in presence of dry ether. So after this addition, what we do is we do hydrolysis. Hydrolysis will do what? Hydrolysis will break this bond. Magnesium plus will take the OH minus of water, and O minus will take the H plus of water, giving rise to the production of alcohol. But the degree of alcohol will be increased. Why? Because this carbonyl carbon is introduced with one more alkyl or aryl group produced by the Grignard reagent. Now, such questions are very, very, very famous for JEE. For example, I have formaldehyde. Now we very well know what is formaldehyde. Sir, if I have a carbonyl carbon and both carbon are hydrogen, so this is the simplest aldehyde called formaldehyde. Now, we do not have to do that mechanism step by step. Just in the mind you can do. I'll tell you how. With methyl magnesium bromide, you tell me what is R minus, sir? Methyl group with a negative sign. So CH3 minus will be produced by CH3 MgBr. This CH3 minus will be getting attached to this carbonyl carbon. Once this carbonyl carbon, which is having two hydrogen, it is getting attached with the methyl group from the Grignard reagent. This double bonded O will become single bonded O minus, and after hydrolysis you do not even have to show the intermediate. For boards, if sometime board is asking, you draw that intermediate. Else, you know, after hydrolysis it will get H plus of water, and the MgBr part will be removed as byproduct taking OH of water. So why draw that product? We have drawn that product in the mechanism so that you may draw the product directly over here. So what you have got a 1 degree alcohol. So formaldehyde always produces 1 degree alcohol with any Grignard reagent. Similarly, if we have higher aldehydes, like if we have acetaldehyde, so this carbonyl carbon will definitely have one hydrogen because it's an aldehyde. But now this group is an alkyl group. So this is CH3CHO. So this is acetaldehyde. Acetaldehyde is getting attacked by what? Now this is benzene ring, the phenyl. So this is phenyl magnesium iodide in presence of dry ether. So this will act as a minus. This minus will be attached to the carbonyl carbon. So I have this CH originally having this methyl group. Just now phenyl has been attached through the Grignard reagent, and the double bonded O after hydrolysis becomes OH. So this will be your product, which will definitely be a 2 degree alcohol. And last, if you have a ketone, let's say I have acetophenone. So we know acetophenone is a carbonyl carbon, a benzene ring attached to it, and CH3. So this general name of this ketone is acetophenone. So this acetophenone, when treated with ethyl magnesium bromide, so this C2H5 minus will be the nucleophile in this case, getting attached to this carbon. Benzene, as it is ethyl group, recently introduces via Grignard reagent. Methyl, originally present. Double bonded O becomes single bonded O minus, and post hydrolysis it becomes a beautiful 3-degree alcohol. So aldehyde forms 1 degree. What aldehyde? Formaldehyde. Rest all the aldehyde forms 2 degree, but ketone forms 3-degree alcohol with Grignard reagent. And for Grignard reagent, you can use any Grignard reagent, even aliphatic, even aromatic. Moving to some questions from mains. So the first question says that this is an alkyl halide reacting with NaOH in presence of C2H5OH, forming product A. Now this product A reacts in two ways. We know this is acidic hydration, and we know this is hydroboration oxidation. So you tell me, acidic hydration and hydroboration oxidation produces product B and product C, and you are given option. This is a JEE Mains 2024 question, so direct application of what we have seen of in JEE Mains. But again, I told you, you can do, after learning that mechanism, question becomes very easy for you. Now, so with the question only, you can think that this product A should be an alkene, because only addition of water takes place to a unsaturated system of alkene. So can you think of from alkyl and aryl halide, can you think of a reaction alkyl halide subjected to this? Sir, this is nothing but alcoholic KOH. Although we know alcohol is not a strong acid than water, so they will not undergo this salt acid base hydrolysis, which is C2H5O minus and Na plus for water, because we know this reaction is highly reversible. Agreed. I say that out of 100 molecules, at least one will form this. As soon as this C2H5O minus is formed, it will be a base. As soon as you get even one molecule of this base will do what? This base will do beta elimination. And after this base will do beta elimination, as in this hydrogen will be removed by this C2H5O minus, and this bromine will be gone. So because as soon as this one molecule is gone, the equilibrium of the above reaction will say array. And when product is removed, even one product is there, when one product is removed, equilibrium will be shifting to forward direction, creating one more, then one more, then one more. So because this product A, which is alkene, is not there in the reaction, this product A, which is alkene, is also getting removed because of acidic hydration and hydroboration oxidation. So this is a good question. But if you do not think it to such an extent also, still you can at least predict that acidic hydration and hydroboration oxidation only happens for an alkene. So this should be an alkene. So beta elimination of that guy will produce nothing but, I'll just clear this and write it clearly, because now we further have to react this. So this is nothing but beta elimination of this will create prop 1ene. Now because this is acidic hydration, so it will result in a Markovnikov addition. वैसे भी anyhow you know carbocation is stable over here in the second carbon, so this will be your product B, Markovnikov addition, and hydroboration oxidation does anti-Markovnikov addition, so it will result in the formation of propane 1-ol. Let us check the option. B is propane 2-ol, both are not same. B is 2 propanol and C is 1 propanol. So obviously option B is your right answer. Let us check. Yes, option B is your right answer. I hope we are clear till this. Now, good. Moving to the next question. So let us attempt this one. So this 2024 question is again, this is nothing but reagent for hydroboration oxidation. That means B will be an anti-Markovnikov product of this alkene. So Markovnikov will be, OH will be going to this carbon because carbocation will be more getting more inductive or hyperconjugating stabilization. So A will be a Markovnikov product. So this is not a Markovnikov product. This is not a Markovnikov product. This is not a Markovnikov product. So only option A is telling you that this is Markovnikov addition, and that will be anti-Markovnikov addition. So your answer will be beautifully B. Now, if you just remember the first slide without the actual mechanism, you will be making your question for mains, but for good questions you should know mechanisms as well. Again, this is mains, another session for 2024. So this is an alkene, so this carbocation will be more stable. Now if I'll have a carbocation over here, then rearrangement can take place. So look at the options. This is mercuration, demercuration. So without rearrangement, it will give us Markovnikov product. So OH will be going to this side. So A, but here the options are not even asking for the product. They are just asking for Markovnikov addition. So A will be a Markovnikov product, and B will be anti-Markovnikov product. So A will be a Markovnikov product and B will be an anti-Markovnikov product. So without moving your pen, you can do your answers. Option will be Bombay. Now, I have to prepare this alcohol, but the question is saying this cannot be prepared by. So here we have to explore the options now. So this is nothing but Grignard reagent. So here, what is there? The benzene. So this will become the minus, and this nucleophile will be getting attached to this carbon. So the carbon which is having the double bonded oxygen will, after hydrolysis, it will become OH. It is having methyl on one side, ethyl on other side, and through Grignard reagent, what will be added? The phenyl group. So look at this carbon, phenyl, methyl, ethyl, and alcohol, because it is getting prepared from this. So this is not an answer, because question is saying which cannot produce that alcohol. So this is getting produced. Look at the option B. So this is our carbonyl carbon having one phenyl, one ethyl, and this is the methyl that will be going. So again, that alcohol will be formed. So this is also not an answer. Without actually doing the complete mechanism, we are able to predict the product. That is the beauty of learning things properly. Now, this is the carbonyl carbon having a phenyl. So one thing is done. Having a methyl. So methyl is also done. So I need an ethyl. This ethyl is provided by the Grignard reagent now. So again, this minus will be going and I'll be getting that product. So obviously answer is Delhi, but let us check what Delhi will form. Now this is just simple formaldehyde. What is the Grignard reagent we are having? Okay, the Grignard reagent is a bulky Grignard reagent, and the minus will be coming on this side. So this minus will be attacking. So let me form that product. Although we know that will not be that alcohol. So let us see what will this alcohol. So this CH2, the aldehyde having double bonded O, this O after hydrolysis will become OH. This carbon, this CH2 from Grignard reagent is getting attached to that carbonyl carbon having this CH, which is having two branches. One is a methyl branch and one is a benzene ring. So obviously this alcohol is not that alcohol. It's an isomer, I guess. So not a product. So an answer for us. Moving to the next question. The next question says again, these all are JEE mains question, guys. So pay huge amount of attention. Good for your boards also, good for your mains also. So now this is an alkene. So first we are, so the BH3 will do what? I've told you, actually it is B2H6 in presence of THF, but question can ask you in ultimately B2H6 in presence of THF when C is an alkene breaks into BH3, and as BH3 molecule it attacks alkene. So even if the question is offering you BH3, it is not doing incorrect. So this BH3 after H2O2 in basic medium will do what? Will do anti-Markovnikov addition of water. So this alkene, when undergone anti-Markovnikov addition of water, OH will be coming to this side and hydrogen will be getting added to that side. Now, this is the alcohol that we have got. After HBr, now we know that 1 degree carbocation is not stable. It is not at all stable. So it is not formed. So because there is no repulsion also. So this HBr as in Br minus will do what? This will do a simple SN2. And once SN2 is done, it will give you a simple substituted alkyl bromide. Now, this alkyl bromide, when reacts with magnesium in ether, so this is a concept of alkyl halides. See, I told you what means does is it recollects two chapters and then frame a question like this one. Now you know you should know alkyl halide also, because from alkyl halide we have seen any alkyl halide when reacts with metal, as in when reacts with magnesium, it forms Grignard reagent. So phenyl CH2, that magnesium will be coming in between because it's a divalent metal, and you will be getting a Grignard reagent. So here we have formed the Grignard reagent. And this Grignard reagent, when added to formaldehyde in presence of dry ether. Now here they have not mentioned dry ether. Now this is your common sense, that first react with this and followed by hydrolysis. So this is what I'm telling you. You should know the predictability of a question also. They may not give you the exact picture of reagent which you have through your theory, right? So common sense has to be used. So this is the Grignard reagent. So we very well know this will be the minus. This minus will be attacking where? This minus will be attacking the CH2 double bond O, which is carbonyl carbon of formaldehyde. So this minus will be attacking this carbon, and I am not having place, so let me write that over here for you. So this phenyl followed by two CH2s. One CH2 is getting added from this carbonyl carbon, and that carbonyl oxygen O after hydrolysis will get hydrogen from water. So this will be your product alcohol. A beautiful question, and I guess our answer is also clear. It is D, but a beautiful question from combining all the facts that we have read, the mechanisms that we read, combining it with the concepts of alkyl halides. Moving forward. Now, this question says a sample of 4.5 milligram of unknown monohydric alcohol. So monohydric alcohol, as an alcohol, is having one OH, was added to methyl magnesium iodide. So I have an alcohol, a monohydric alcohol, added to CH3 MgI, and it is saying a gas is evolved. Now, look at this question. A very beautiful question asking you the common sense of Grignard reagent. Now we know, I've told you in the initial slides in the mechanism also, that Grignard reagent only reacts in presence of dry ether with carbonyl compounds. So why? Because Grignard reagent has this beautiful minus, because magnesium is a highly electropositive metal. It will make even this carbon electron rich, and this electron rich carbon can have H plus from any weakest acid. Now alcohol is not an acid. Water is a very strong acid in comparison to alcohol. Although we know, if we talk of mineral acids, water is just a solvent. It dissociates very slightly, but these organic acids are so weak. But still, these weak acids at least have very little capacity of having H plus. So whoever, if a traces of a molecule are present which can furnish H plus, so Grignard reagent will not react with anybody else. Rather, they will take that hydrogen and this CH3. Okay, I'm sorry, this is not CH3 plus because of magnesium plus, it is CH3 minus. So this CH3 minus will take up the hydrogen of alcohol and will form methane gas, which will be evolved, leaving behind whatever else we have. So magnesium having one iodine, so this highly electropositive +2 metal will now have the alkoxide ion, because plus requires minus, so it will be searching for all the possible minuses. So that's why Grignard agent is only reacted in presence of dry ether. If any species present that can furnish H plus, this R minus, the alkyl or aryl part gets attached with that hydrogen and a hydrocarbon is produced. We have done this in hydrocarbons as well, so a concept of hydrocarbon also. So what will be the gas? Sir, methane. Now this question is talking about the stoichiometry thing, that is mole concept logic is now applied. So we know if I have n moles, because this is a balanced reaction, so n moles of this will produce n moles of this, because stoichiometrically 1 will produce 1. And question is telling you that this gas as STP is measured how much, it is this much ml. So number of moles is equal to volume occupied by gas upon volume occupied by 1 mole of gas at STP is how much? It is 22.4 liters, but 22400 ml, because given volume is in ml. So ml will get cancelled. So if this is the number of moles of methane produced, then number of moles of alcohol will be same. And because this is having only one OH, so stoichiometrically it is 1:1. Now we know the number of moles of alcohol. Weight of alcohol is given, and what are we asked in the question? Molecular mass. So use the formula of number of moles. So number of moles is also equal to weight of substance, which is 4.5 milligram. 4.5 milligram as in 4.5 into 10 to the power minus 3 gram upon molar mass, that we have to determine. It will be equal to that number of moles we have already calculated for methane, which is number of moles of alcohol also, which is equal to 3.1 upon 22400. Now in order to calculate molar mass, now what students do, they start solving. Use common sense also. Sir, how? See, this is 31, this is 45. 15 2 ja 30, 15 3 ja 45. Now this is definitely greater than 2, so keep that thing in mind. So m will be equal to 3 by 2 into this thing, which is 2 to 0.4. Why 0.4? Because 10 to the power minus 3, so this will become 22.4. Now this is nothing but 11.2, so thrice is 33.6. But your molar mass will be, because this is not 3, this is not 2, this is more than 2. That means this is not 2, this is something more than 2. That means answer will be, denominator is more, so answer will be lesser than 33.6. So what is an integer lesser than 33.6? So do not go for 34, instead go for 33, or else you can definitely calculate also. The answer that you will be getting is 33. Let me check that answer for you. Yes, answer will be 33. So for calculations you should do some common senses also, which shall save your time. Now coming to the preparation of alcohols, we have done. So coming to preparation of phenols. Now in order to form phenol, there are basically 4 very important methods. First method of preparation of phenol, which we have already seen in alkyl and aryl halides, the famous Dawes process. The reaction of aryl halides. So whenever aryl halides are reacted with base, sir, we know that because of partial double bond character, that C bond X does not break. But if this OH minus is given so much power as in vigorous condition, a high temperature of 350 degrees Celsius, extreme temperature of 300 atm pressure, then at such vigorous condition, even this minus will be attacking the very less delta positivity, but because of this excess of temperature and pressure, this C bond Cl will be broken and you will be getting a phenol. But because medium is basic and we know phenol is a stronger acid than water, so neutralization will take place. So what product you will report? You will report a salt. The salt will be sodium phenoxide. And if you kill the basic medium, as in if you do acidification, so acid will neutralize the excess of base and you will be next getting phenol as your major product. The famous Dawes process, which says reactions of aryl halide are quite different from alkyl halides because of the same reason, the resonance nature. So because of that, the partial double bond character has been increased and it is very difficult to break this C bond Cl. The similar logic we have seen in alkyl and aryl halides. I'm repeating everything is what I'm saying. Moving to the next preparation of alcohols. So phenols. So phenols can also be formed using benzene. Doing what? Electrophilic substitution. What electrophile I'll use? The sulfonic acid group. So in order to add The electrophile of sulfonic acid, what was the reagent? Oleum. What is oleum? Fuming sulfuric acid, which is nothing but mixture of H2SO4 and free SO3 gas. Combine them, you can also write it as H2S2O7. So hydrogen will be substituted and the electrophile will be getting attached to benzene ring in form of sulfur, which is having very high positive charge, +6 oxidation state. So you will be getting your benzene sulfonic acid. Now we know sulfur is a third period element. The bond length is quite large, and because the bond length is quite large, this bond can be easily broken and a stronger bond will be formed. So even if I treat with basic NaOH, even this basic NaO minus with no temperature, no pressure, is very much capable. Why? Because this bond length of C bond S is quite large. So this can easily be broken and it will be removed. And what you will be getting? Again salt. Why, sir? Because again what you have used? Base. So phenol will be formed. But because phenol is a strong acid, so acid plus base will be forming a salt. So what product you will be reporting? Salt. Post acidification, that is H3O plus, you will be reporting phenol, a very, very, very important term of preparation. Now these are the reactions which mains directly ask. So important for your boards also and will be helpful for mains also. So this becomes the second method of preparation of phenol. Coming to the third method, again done the Sand-Mears reaction. How you form benzene diazonium chloride? Through aniline. Aniline reacts with nitrous acid. Now nitrous acid is a unstable acid, so its bottle cannot be sold, so we make it in the runtime. How we make it? Using a mixture of NaNO2 and HCl. Doing what? Here this nitrogen, which is NaNO2 with HCl, will form nitrous acid, and that nitrous acid gets attached to this nitrogen and you form your diazonium cation, which is a very strong leaving group. You will say, sir, bond length is still small, C bond N, but nitrogen is the most stable diatomic molecule. Nobody can hold nitrogen gas. So why this guy is holding nitrogen gas? Because this pi cloud is in resonance with the benzene ring. So because of resonance effect, this nitrogen is holded by the benzene ring. So aryl diazonium salt can be formed. Alkyl diazonium salt can never be formed, which we will again do in detail while discussing amines, but this is the detail. We'll just draw the resonating structures again, but still you can know that, because you know the knowledge of GOC, that because of resonance this will have a partial double bond character, and therefore this nitrogen gas can be holded by this aryl group, by the benzene group. But still I'm saying, because nitrogen is the most stable diatomic molecule, so what we have to do? Reduce its kinetic energy. Only then this benzene is able to hold this stable nitrogen gas. So in order to reduce the kinetic energy of the gas, what condition we use? Ice cold water, that is 0 to 5 degrees Celsius. And at this situation you form your diazonium salt. Now to this diazonium salt, if we add cuprous halides, that forms aryl halide, done in Sand-Mears reaction. If we just put water now, so sir, water as in just at room temperature, ice cold condition gone. So now nitrogen gas will be removed, creating a positivity at the benzene ring, and now you do not even need a base. Even lone pair of oxygen of water can be getting attached to benzene ring, resulting in the formation of phenol. And see, the most stable diatomic molecule, this nitrogen was of amine, the other nitrogen was being supplied by NaNO2 of nitrous acid. So although you do not need to know such conditions, such detailed condition for mains, but still I have given you, that's I've told you, these notes you do not have to write. Download these notes. That's why I'm using laser on them, so that they, in this short span of time, they will act as your class notes, but you have to revise them again and again. So this becomes the third method of preparation of phenol. Moving to the final method of preparation of phenol. Now the last and probably I would say the most important method of preparation of phenol is through cumene. Now what is cumene? Cumene is isopropyl benzene. When benzene is substituted with an isopropyl group, first carbon, second carbon, and a methyl branch with a free valency, when this is connected to benzene, this becomes cumene, which is isopropyl benzene. Cumene is undergone oxidation. The carbon, the benzylic carbon, as in this carbon having hydrogen, is oxidized by this oxygen, because that carbon is having high, that carbocation, that plus over here is quite stable. So this benzylic carbon is it gets oxidized by oxygen, and you get cumene hydroperoxide. This cumene hydroperoxide can undergo rearrangement in acidic medium. So what we do, acidic hydrolysis of this peroxide. So react with it oxygen, the benzylic carbon gets oxidized, you get a peroxide, this hydroperoxide of cumene, when undergone acidic hydrolysis. First, I'll give you the detail which is more than sufficient for your board and mains type of questions. So first, react with oxygen, followed by acidic hydrolysis, will result in the formation of phenol. And what about the other species? One oxygen will be going to this benzene ring, and this carbon becomes the carbonyl carbon, so it will get a double bonded O, resulting in the formation of acetone. Now, for good questions, let's say if I ask you, for mains questions, I mean this much knowledge is sufficient, but if a good question in mains also they had come, that if I have a substituted benzene, then with substituted benzene will get what oxygen. So for that you should ultimately know the mechanism. So for good questions I'm telling you, so that's why I've given you that basic first, and now the mechanism, how this rearrangement is taking place. I've told you it take place in acidic medium. So this H plus is given by, sir, obviously the medium we have here, you must have used some acid. So this H plus will protonate this oxygen at the terminal, the not the first oxygen near to benzene ring, but the later oxygen. That oxygen gets protonated, the lone pair is given to H plus. Once oxygen attains a positive charge, now it is very angry, it will break every and any possible bond. So when this oxygen gets protonated, it snatches electron of this peroxide oxygen. When electron of this oxygen is gone, whole of the ring is electron rich, yes, a pi cloud. If I have more substituted ring which is having plus R group, it will be doing it to a larger extent. If I'm having a benzene ring which is substituted by electron withdrawing group, then it will be restricting this benzene ring to give electrons. So this mechanism will help you for those questions. So this electron rich benzene ring will give the electron to this oxygen, resulting in the formation of a rearranged product. So the first oxygen, the two oxygen added via oxidation, one of that green oxygen is removed in form of water, and this benzene has recently been introduced to the remainder oxygen that was added in the first step, resulting in the formation of positivity, as in carbocation, at this particular benzylic carbon. Now this carbocation is stable. Why we are saying this? Because this carbocation is stabilized by the resonance of this oxygen lone pair, and this lone pair is also getting resonance stabilized by whole of the benzene ring. So this carbocation is not unstable, this is resonance stabilized carbocation, hence it will be formed. And when this carbocation, because what we have done, acidic hydrolysis, so water will also be present. So now lone pair of electron of water, oxygen, I mean lone pair of electron of oxygen from water will be donated to this stable carbocation. And obviously the H plus that we have taken from the reagent is given back by this water, and OH is getting attached to this carbonyl carbon. Now remember, there are two oxygen that has been introduced, but one oxygen is through this and one oxygen is through solvent water, resulting in the formation of this. Now post the formation of this, if medium is still acidic, so this oxygen lone pair will again get protonated, and again oxygen has got a positivity. Now which bond will be easily broken? O bond C of benzene or O bond C of alkyl carbon? O bond C of benzene will be resonance stabilized. So bond order will be more. So this bond is relatively less stable. So post this, the oxygen will snatch the electron of this alkyl carbon, and this guy will be getting into the shape of phenol. So this is one of the major product, the phenol, because of which we have done this process. And what about this one, sir? Once carbon has been snatched, so once electron of carbon has been snatched by this electronegative oxygen, who pays the price? uh, the scapegoat. What is the scapegoat always in organic chemistry? Chotu sa hydrogen. So electron of this hydrogen is snatched by oxygen and given to this carbon, resulting in the formation of this carbonyl group. So this is your acetone and this is your phenol. A very beautiful mechanism, a very beautiful rearrangement, I would rather say, which you should only know for your advanced question, else you can skip this. The important part of cumene forming phenol along with acetone I've already shared in the beginning only. So moving to the properties of alcohol and phenol, we have preparation of alcohols and phenols we have done. Now moving to preparation of ether, we will do later, because ether reactions of ether are nothing. If we read reactions of alcohols, preparation of ether and then ether will be easily studied. That's why NCERT had also made this thing a point that they have given the preparation of ether after the reactions of alcohol. So we will be sticking to that NCERT plan, because that is the holy grail for JEE mains and for whole of the NTA syllabus. Even for JEE advanced, NCERT is the bible for JEE chemistry. Now before going to the chemical properties, let us quickly do some physical properties of alcohol, phenol and ethers all. Now, what about boiling point? Sir, we definitely know more mass will have more boiling point. We think of intermolecular forces of attraction only when molecules are of comparable mass. So when they are of comparable mass, what is the strongest intermolecular force of attraction? Hydrogen bonding. So alcohols can do hydrogen bonding. Ethers can do dipole-dipole attraction. Alkanes are non-polar, so they do London dispersion forces, the weakest intermolecular force of attraction. So if you compare comparable mass compounds, who will have highest boiling point? Obviously alcohol, followed by ether. And who will have the least boiling point? Obviously alcohols. If we compare isomeric alcohols, then we have done this in the previous chapters. I'm just summarizing that everything for you. If I have isomeric alcohols, a straight chain alcohol will have more surface area, so we'll have more boiling point, because more be the surface area, more is the extent to do intermolecular forces of attraction. As the surface area reduces, as branching increases, surface area reduces, molecule become compact, so boiling point decreases. So for isomeric alcohols, boiling point is inversely proportional to branching. We will see many questions relating to this concept also. Talking about solubilities, or organic compounds are non-polar, but alcohol is having a tendency to form hydrogen bond, and because of that, so due to hydrogen bond, alcohol and phenol are relatively soluble. Relatively as in, if you compare with them with other organic compounds like ether, alkyl halides, alkanes, they are quite soluble in water. And obviously this solubility will definitely decrease, because ultimately it is soluble because of OH. The carbon chain is not invited. So 1 carbon, 2 carbon, 3 carbon can be made soluble, but as you increase the number of carbon chains, solubility will keep on decreasing, because it cannot do hydrogen bond, only OH can do hydrogen bond. So this is a very basic fact which you should know. Now moving to the important section. I mean, preparations were also important, but after physical property, the most important section is the chemical properties. Now, first, let us discuss the chemical properties of alcohols. So we know, sir, alcohol has two bonds that can be broken, C bond O and O bond H. So when alcohol act as a nucleophiles, O bond H is broken. If O bond H is broken, that means alcohol behave as an acid in such cases. But you should know this, when alcohol act as a nucleophile. Now what is a nucleophile? Plus loving species. So what is alcohol? Alcohol is having oxygen. So the lone pair on oxygen of alcohol make it electron rich also. So if it is offered with a electron deficiency even by a carbocation. Let's say if it is being treated by a species which has created a carbocation, so these lone pair of electrons will be attracted to this carbocation. So you tell me, alcohol is doing what? Alcohol is giving its electron to a positive carbocation. So this alcohol is behaving as what? It is a plus loving species. So when alcohol behave as a plus loving species, as a nucleophile, let us draw the structure. This carbon was a carbocation, so it was a trigonal planar species. Once oxygen of lone pair of oxygen has attacked this carbon, it becomes a tetrahedral species. So mentioning that tetrahedral species, these three bonds will be as it is. It has just been introduced now. Because now oxygen has got positivity, it will not think of anything. It will break the weakest bond. Who is having the weakest bond? O bond H, because hydrogen is always the scapegoat. The electron of hydrogen is snatched and you get a ether substituted product. So this is how you can form ether also. And over here you tell me what bond is broken. So O bond H cleavage takes place whenever alcohol act as a nucleophile. Some people ask, sir, why can't C bond here, even the C bond O can be broken? That's why I told you C bond O is a very strong bond. It is formed by atoms of it is formed by electrons having almost similar energized orbitals. So bond formed between similar energized orbital are not stable. C bond O is very stable, so it is rather very difficult to form C bond O. So sir, that means C bond O can never be broken? No, it can be broken, but it can be only broken when you have protonated alcohols, because normal alcohol cannot, but protonated alcohols can definitely behave as electrophile, as an electron deficient species. I tell you how. Now this is a phenol. Let's say this phenol is introduced with some acid. Again, the first step is taking place here. The electrons of oxygen were being donated to a carbon. If the medium is acidic, it will be donated to an H plus, and this alcohol will then form a protonated alcohol. Now this protonated alcohol, once I have formed a protonated alcohol, there may be a case that because there was an acid, so after giving H plus, there will be the presence of a conjugate base also, an electron rich species will be present. If that electron rich species is willing to give electron, then in that case C bond O will also C bond O can also be broken, and this whole thing will be removed as water, and this will give rise to a simple substituted product by this conjugate base. And again, now alkyl halides logic will be used. Why? Because it can be even SN1 substitution, it can even be SN2 substitution. Over here, because this carbocation is not having any stability, it will just be a 1 degree carbocation, so rather I'm preferably forming a SN2 substituted product. But for ethers, I'm telling you, whenever we get such a case, you definitely form a carbocation, but 1 degree carbocation is not stable, it is unstable. That's why whenever we form a 1 degree carbocation, we try not to form it, rather do the substitution via SN2, where no carbocation is formed, a backside attack takes place. That's what we have done over here. But what I'm concluding with this slide, when alcohol act as a nucleophile, O bond H is broken. When alcohol cannot act, but protonated alcohol act as electrophile, C bond O is broken. So chemical reactions of alcohol will be divided into two halves. First set of reaction will be reactions involving O bond H cleavage, and second set of reaction will be reactions involving C bond O cleavage. Now let us move to the individual sections of chemical reactions of alcohols. So the first set of reactions involving cleavage of O bond H is definitely capital A, the acidic nature of alcohols also and phenols also. So there are some reactions which are given by both aliphatic and aromatic alcohols, where the first reaction is definitely, we know this through class 10th, reaction with metal. Any active metal like alkali, alkaline earth metals, aluminium, they are active metals. So these active metals react with any sort of alcohol, either aliphatic or aromatic. They forms their corresponding salt, the alkoxides or the phenoxides, and obviously hydrogen gas is released. So metal plus acid forms salt plus hydrogen gas. These, all the active metals can do this. Now, but if we compare the acidic nature, then yes, extent of acidic nature will be different, and it will be governed by all the concepts of GOC which we have already learned. So let us revise that. Acidic nature, sir, we know who is an acid, who has a capacity to accept electron. When my capacity to accept electron will increase, when electrons will be removed from myself. So all the electron withdrawing group will increase the acidic nature, and inversely, if I have electron donating group, then my electron deficiency will be getting satisfied, and if at all it is getting satisfied, my acidic nature will be reduced. So acidic nature is inversely proportional to electron donating group. We know this through GOC. Again, we will be seeing number of questions just on the basis of this application, but first, comparing the acidic nature. On the first point, we are comparing the acidic nature of what? We are comparing the acidic nature of among aliphatic alcohols. Now, as we know, these alkyl groups do what? They have plus I effect. So, because of that electron donating nature, 3-degree alcohol will be least acidic, followed by 2-degree, and obviously the methyl alcohol, which is not defined, the degree of methyl alcohol is not defined, so it will be strongest aliphatic alcohol. Coming to the next capital B set of reactions, where we are discussing to the acidic nature a bit more. We obviously know this also, that if we compare the acidic nature of aliphatic alcohol with water, then what is neutralization through equilibrium? Also, we know, we generally say that a base when reacts with an acid, and over here we are comparing the acidic nature of alcohols. So if a base reacts with acid, generally neutralization takes place and it forms salt and water. But alcohols, aliphatic alcohols, they are having a capacity to break O bond H. But if their acidic nature is compared with water, they are even weaker acids than water. So if they are weaker acid, then neutralization cannot take place. Obviously the reaction do proceed to forward direction to a very limited extent, and hence what takes place? Reversible reaction. So this salt in fact reacts with water and undergoes salt hydrolysis, forming base and alcohol. So alcohol do not give neutralization reaction. We have to remember this. Now, giving it another common sense, what is the base over here? If this reaction is happening as in backward reaction is highly favorable, that means this RO minus, I just use a laser so that I do not disturb your notes. This RO minus, it behaves as a strong base. Now you give me with your common sense, does this alkyl group apply plus I effect? Yes. If I compare a hydroxide ion given by NaOH, does this hydrogen has any capacity? No, sir. Alkyl group is having higher plus I with respect to what? Sir, plus I or minus I is defined with respect to hydrogen only. So this H is having no power, while this alkyl group applies a plus I effect, thereby making this RO minus a stronger base. So if it is a stronger base, it will give electron, and if it gives electron, then this base brings the reaction to backward direction, while OH minus is a weaker base than the alkoxide ion. And this also signifies that aliphatic alcohol are weaker acids than water. So ultimately, we are making a conclusion after this that all the aliphatic alcohols are weaker acid than water. If I am a stronger acid, I would be having a higher value of Ka. If I'm a stronger acid, I will be having a lower value of pKa, because pKa is minus of log of K. These things are very important for questions. Now, why I'm giving you more space over here? Because there is an experimental fact on the basis of this value of Ka. It has no other explanation. It's just a conclusion through the experimental data. As we have already seen, among aliphatic alcohol, what was the strongest acid? Methyl alcohol, which is not even 1 degree. It's the strongest aliphatic acid, and once we have gone to the value of Ka of methanol, it is experimental fact that this methanol is actually even stronger acid than water. But for generalization, we will always say that alkoxide ion are stronger base. And why they are stronger base? Because all the aliphatic alcohol as an ROH are weaker acids than water. That's why I'm saying over here this RO minus is a strong base. If it is a strong base, then its acid, which is ROH, will be a weak acid. Then whom? If OH minus is a weak base, then its conjugate acid, that is H2O, will be a strong acid. So generally we will always say that water is a strong acid than all aliphatic alcohol. But yes, if question is asking us precisely, then we should know this theoretically through the value of Ka, that yes, methanol is one aliphatic acid which is slightly stronger acid than water. Comparing the acidic nature of phenol, we know that this phenoxide ion is resonance stabilized. We have already made those resonating structures, so I'm not going to make it again, because we have even discussed this in stretch in GOC as well. So, but I'm summarizing it again, because for alcohol, you should know this much. Your mains question will be more than sufficient. Yes. If we compare acidic nature for advanced question, we have to move some steps forward, but those are question specific things. The theory, this much is more than sufficient, and this is more than sufficient for your mains level of questions also. So we'll be discussing those questions as well. Now, let us putting summary to it, that phenoxide ion is resonance stabilized, and because this conjugate base, this conjugate anion is resonance stabilized, therefore equilibrium will be shifting to forward direction. Therefore I have just made this arrow signifying that the previous reaction, alcohol do not give neutralization, but yes, phenol gives neutralization. So they react with base and form salt and water. That signifies that all the aromatic alcohols, so overall order of acidic nature, what I'm concluding, that phenols among alcohols and waters, phenol are the strongest acid, followed by the one aliphatic acid, which is methanol. Post that you have water, and all of the remaining aliphatic acids are weak acid than water. Now this is an exact order which you should always keep in your mind. Coming to some specific questions which I was telling you. Now the first question says, these are all JEE mains question, my friend. So take a good look at them. Now, assertion says alcohol react as both nucleophiles and electrophiles. We have started this, so this is definitely correct. The assertion is correct. Now, reason it is saying alcohol react with active metals such as sodium, potassium and aluminium to yield corresponding alkoxide. This is also a correct statement. But why alcohol react as both nucleophile and electrophile? The reason, when lone pair of electron is given to C plus, then O bond H break. O bond H break, this is the reason for O bond H cleavage. I mean, this is one of the application of O bond H cleavage, but this has nothing to do with the cleavage of C bond O, where alcohol act as electrophile. So yes, assertion is also correct, reason is also correct, but obviously it is not a correct explanation. So our answer will be option D. I hope it is clear to all of us. Now, moving ahead, now these questions will actually give you confidence that learning the basics of NCERT are more than sufficient. Now this is also a JEE question which says, among the following, which one will react with base, dilute base? So who reacts with base? An acid which is stronger than water. So this is benzylic alcohol, although it is containing benzene, but this OH is connected to an sp3 hybridized carbon. So this also becomes an aliphatic alcohol. So all aliphatic alcohol are weaker acids than water. So no neutralization. Aliphatic, so no neutralization. It is a 3-degree alcohol, so it is very, very weak acid. And obviously, phenol is the only alcohol who is stronger acid than water. Therefore, it will undergo neutralization. Moving to now. Again, the question of pKa. So again, if acidic nature is high, then Ka value will be large and pKa will be smallest. So let us first do the acidic nature. This is normal phenol. This is NO2. Now remember, we have done this for aliphatic alcohol. So for aromatic, it will also be valid. What? Electron withdrawing group. Who is the most electron withdrawing? What is the most dominating electron displacement effect? First, we always see resonance effect. Post that, we see hyperconjugation. And last, we see inductive. Because in resonance, the actual delocalization of electron takes place. In hyperconjugation also, actual delocalization of electron takes place, and in inductive, no actual delocalization. It is just partial shifting of the sigma electron cloud. So extent of inductive is the weakest. So inductive we see at the last. Now, because NO2 applies what effect? It applies minus R effect. But it applies minus R effect where? At its ortho and para position. So because this OH is para to NO2, so this act as a minus R group, creating positivity at ortho and para position. So this alcohol will be feeling electron is getting withdrawn by what nature? By resonance nature. So this is a strong electron withdrawing group, and electron withdrawing group does what? Electron withdrawing group increases acidic nature. So this is strong minus R. Yes, this is not, this is meta position, but yes, definitely it will be applying a strong minus I. This phenol is having nothing, so it is having just hydrogen. And this oxygen, because it is having lone pair of electrons and it is not having any vacant orbital, so it will be acting as a plus R group, and plus R group is an electron donating group. So electron donating group decreases acidic nature. So who will be, if I do the acidic nature, then who will be the strongest acid? Sir, Bombay. After that, C. After that, at least phenol is not having any electron donating group, so basic phenol is better, and this electron donating group will in fact make it weakest acid. So D will be weakest acid, but this is the order of acidic nature. Question is asking you the order of pKa. So order of pKa will be reversed. So D will be having highest. So D is having highest. Bombay is having lowest. So this is gone, and obviously Bombay is lowest. Post that we have CA. So option is option Delhi. I hope these questions are clear to you, and these are very, very, very probable questions. Moving to the next question. The next question again asks you to give the acidic nature. Let us see. It is giving you the acidic nature only, not pK and that pK or K. So again, I hope now this question is quite clear to us. This is electron withdrawing group. So EWG, good acid. No, this is plus R. So electron donating, gone case. This phenol is even better. This is also having 2. In fact, this is also minus R. This is also minus R. So who will be strongest acid? E. After that, Bombay. So E will be strongest. So E is strongest. Every option is saying E is strongest. After that, Bombay is strongest. So this is gone. After that, phenol, because C is having a plus R group. So electron donating group decreases acidic nature. So in fact, having nothing is better than having an electron donating group, because electron donating group decreases acidic nature. So after that, D will come. So E, B and D, E, B and D, E, B and D. After that, C will come, because C is ultimately phenol. Whoever, if you decrease electron donating nature of phenol, but at the end of the day, it is phenol. So phenol as a functional group is a strong acid than any type of aliphatic alcohol. So A will be the weakest. So A will be the weakest, and then C will be coming. So here also, what is your best possible answer? Option D. Moving to the next question. The next question compares about the ortho. Meta and para-nitrophenol are very, very famous example. Why? Because we have recently seen, and definitely we know this through GOC also, that if I have phenol over here, then this phenol, when substituted by NO2, where if it is at ortho position, it can be at meta position, it can be at para position. Then we definitely know at ortho and para position, this NO2 acts as a strong minus R group, but there's a catch. In case of orthonitrophenol, actually, there is a beautiful case of intramolecular hydrogen bonding. So actually this hydrogen is attracted by the oxygen electronegativity, and because it is attracted, so its ability to be removed decreases. So because of intramolecular hydrogen bonding, this hydrogen is in fact holded by the NO2 unit, and if it is getting holded, it will not be getting furnished. So its acidic nature will be reduced. So most acidic isomer will be the para isomer. Let us look at the statement. It is saying para-nitrophenol is more acidic than meta and ortho. Yes, meta, with meta it is definitely better, because at meta there is no resonance, it is just minus I, it is minus R. So obviously para is much better than meta, but it is even better than ortho. Why? Because ortho involves intramolecular hydrogen bonding, a very, very, very important case. Also, we know this through chemical bonding, that because it is involved in intramolecular hydrogen bonding, so its boiling point will be less, and whoever species is having lesser boiling point, it will be termed as more volatile substance. So this will be a more volatile substance, as in it can be easily, boiling point is less, so it can be easily boiled, it can be easily vaporized. It is a more volatile substance, and hence ortho and para-nitrophenol are easily separated by each other through steam distillation, because this can even be boiled using steam. You do not even have to heat, just provide steam. With steam, this orthonitrophenol gets away because its boiling point is very less. So these two are steam distilled and separated from each other, because this guy is having very less boiling point. On the other hand, this guy will have intermolecular hydrogen bonding, so it will have a relatively higher boiling point, and therefore it cannot be vaporized, it cannot be made into in gaseous state by just steam. This goes out with steam, so they are steam distilled from each other. Now these are some very important facts. Now, so statement 1 is definitely correct. Now coming to statement 2, statement 2 says ethanol give immediately turbidity with low-cast agent. Now this is a concept from alkyl and aryl halides. We know every alcohol react with concentrated HCl in presence of anhydrous ZnCl2. In presence of anhydrous ZnCl2 behaves as a Lewis acid, and the mixture is known as Lucas reagent. They produce alkyl chloride. Whenever alkyl chloride is produced, we can see that alkyl chloride, how it creates a turbidity, and which alcohol creates instant turbidity, which can form carbocation easily, which alcohol can form easily stable carbocation, 3-degree alcohols. So actually 3-degree alcohols gives turbidity instantly. In fact, 1-degree alcohol do not react with Lucas reagent, but yes, if you get after it, then it reacts, but by heating for till 30 minutes. We remember that through alkylide, and this option is saying ethanol gives immediately. So immediately is given by 3-degree alcohols, not 1-degree alcohol. So statement 1 is true, but statement 2 is false. So our answer will be 1 is true, true is false. Option A. Let us check this theoretical. It is showing option A only. So I hope we are clear with this. Okay, I guess it is not getting moved. Okay, so I hope we are clear till this. Now moving to the next question. The next question, now whatever we have discussed, it is explaining that only. What is it is explaining? It is saying orthonitrophenol is steam volatile due to, yes, it is having less boiling point because of intramolecular hydrogen bonding, and hence it is steam volatile due to what? Due to intramolecular hydrogen bonding. So this is definitely true. Statement 2 says orthonitrophenol has higher melting point. Now We have done this in aryl halides also. The similar fact will be applied. If you compare their boiling point, then their boiling point are almost comparable. But yes, what do you melt? We melt a solid. And para isomers are known to have symmetrical packing. So para isomer have relatively higher melting point than both ortho and meta isomer. It is saying orthonitrophenol has high melting point. No. Which one is more symmetric? Para. So statement 2 is definitely false. So 1 is true and true is false. That means option D is your right answer. Let us check this also. Yeah. Moving to the next question. Now, the next question again discusses about, I hope we have done a similar question. So let us, I guess you will attempt this question by yourself. So give it a try. So I hope all of you got the answer for the repeated concept. Let us make the acidic nature order. So obviously paranitrophenol, because of minus R, becomes the strongest acid. So D becomes the strongest acid, followed by C, which is metanitro. It'll only have minus I, followed by phenol, which is having nothing, but because it's an aromatic alcohol, so it will be stronger than A, where A is just an aliphatic alcohol, but over here you are given the values of Ka. So who will be having the smallest value of Ka? Smallest value is 7.1. So 7.1 will be given by D, 8.3 will be given by C. The intermediate one, that is 10, will be given by phenol, and the highest value of Ka will be of weakest acid, which is ethanol in this case. So I guess option D will be your answer. Moving to the next question. I hope you have cracked it. Now, next question, it is not a question. Now, what set of reactions we had? We are learning reactions involving cleavage of O bond H. First set of reactions, capital A, we had is the acidic nature. Now, this is in fact capital B, which is the last set of reactions where what bond is broken? The O bond H of alcohols. Now, the famous reaction of esterification, which we I guess know from class 10th, but now we'll be discussing it to a greater extent. Now, we definitely know any alcohol, even it is aliphatic or aromatic. That's why let me not make this notes unclear for you. So let me use a highlighter for you. So this is alcohol where O bond H of alcohol, that means this H will be broken, and when it's react with acid or its derivatives. What derivatives? Acid anhydride or any of acid halides. When they react, what is produced? The classic preparation of ester. Now, how ester is produced? The hydrogen of alcohol and the OH or the substituted part of OH. So how do you get acid derivatives? When this OH is substituted by another carboxylic acid unit, it becomes acid anhydride. When it is substituted by any halogen, the famous is chlorine, so acid chloride. So these are acid derivatives. So how ester is formed? H of alcohol and OH and substituted part of carboxylic acid. They are removed as byproducts and you get your beautiful ester. Now, this is a basic, I guess you know this basic from class 10, but adding some more information to it is, generally esterification is done in acidic medium and it is a highly reversible reaction. It proceeds forward to a very small extent. So according to Le Chatelier's principle of equilibrium, if you want the product to be produced in larger extent on an industry, what you'll do? You remove the byproduct. So if I remove this byproduct, then equilibrium will be shifted to forward direction. The same principle has been applied in case of acid halide, where instead of this H plus, we have used pyridine. Pyridine, the nitrogen, the lone pair on nitrogen of this pyridine is not involved in resonance, hence it is a very good base. So this base reacts with the acid produced and forms salt, shifting the equilibrium to forward direction. Therefore, over here I have not used a reversible sign because this reaction is largely proceeded in the forward direction. So in the third step, percentage of ester produced is quite high. Now, one of the very famous practical example of esterification is the formation of aspirin. Now, why aspirin is important? Because it is a bukhar ki dawai, antipyretic, which reduces fever, and it is a powerful dard ki dawai as an analgesic, which reduces pain. So this aspirin is nothing but it is acetyl salicylic acid. Now, what is salicylic acid? It is a very famous general name for a carboxylic acid which is substituted by alcohol at its ortho position. So this ortho substituted benzoic acid is generally named as a very famous name. It is called salicylic acid. Ultimately, it is having alcohol. The hydrogen of alcohol is reacted with acid anhydride. What acid anhydride I'm using? The anhydride of acetic acid. So it is acetic anhydride. The reaction takes place in acidic medium and you get your acetyl salicylic acid, which is nothing but generally termed as aspirin, which is a powerful antipyretic and analgesic, a very famous reaction. And the byproduct is obviously the substituted part of carboxylic acid. The OH has been substituted by this acetyl group. So this acetyl group goes with the hydrogen of alcohol, forming acetic acid as byproduct. Now, one point that I am adding over here is the mechanism. You will say, sir, this is mains, why you are discussing this? Mechanism is even given in NCERT. But it is given in the chapter of carbonyl compounds. Why? Because if somebody, for good questions, if somebody is going to ask you which acid, for example, we have already seen this, that what is broken? O bond H of alcohol. So that means this is an acidic nature of alcohols. So which alcohol gives esterification faster? Methanol or ethanol? Sir, methanol is a stronger acid, and because O bond H is going to break, so the alcohol which is a stronger acid will give faster esterification. This you can definitely think without learning the mechanism, because you have read that O bond H of alcohol is broken. But people will ask you sometimes, for a good question, that although carboxylic acid is a strong acid than alcohol, than any of the aromatic and aliphatic alcohol. So if carboxylic acid is strong acid, then it should give H. It should give H plus. How come alcohol is giving H plus? One question is that you are clueless if you do not know the mechanism. Also, if somebody is going to ask you formic acid or acetic acid, which is an acid which gives esterification to a larger extent. So for that questions, you need to learn the mechanism. So let us just know the mechanism, and then I'll link it with the topic of carbonyl compounds here only. Now, first of all, why we need H plus as a catalyst? In order to protonate this carbonyl oxygen, because carbonyl oxygen, we very well know carbonyl group is a very polar molecule, polar group. So this excess of electron which is present in oxygen gets protonated by the catalyst H plus. So you get this protonated acid. Once you have a protonated acid, we know oxygen is an electronegative element. Once it attains a positive charge, it will definitely snatch electron and will try to neutralize itself. Once this pi cloud is snatched by this oxygen, you get a positivity at the carbonyl carbon positivity, as in now this positivity will attract minus, and the minus is the lone pair of electrons on oxygen of alcohol. So this becomes a nucleophilic addition. Who is the nucleophile? Who is the plus loving species? The lone pair of electrons on oxygen. So alcohol acts as a nucleophile and gets added to this carbonyl carbon. So whatever increases the rate of reaction of this nucleophilic addition is our answer. If I have formic acid, then the first is the steric factor, because hydrogen is too small. Alkyl group will create crowding. So if they create crowding, the attack of alcohol will be hindered. So because of steric factor also, what will be more reactive, formic acid or acetic acid? Formic acid. Point number 2, whatever increases the delta positivity on this carbon, whatever increases the positivity on this carbon will influence the lone pair of electron on oxygen to react to a faster extent. Therefore, this electronic factor also tells you that if I have electron withdrawing group, over here, then positivity on this carbon will be increased. On the contrary, if I have electron donating group, like if I have a CH3 group over here instead of hydrogen, it will give plus I. So this plus I will try to reduce this positivity. So this attack of lone pair of electron of oxygen of alcohol will also be getting reduced. So because of both these factors, the electronic factor, which is most dominant, followed by the steric factor, because of these two factors, which acid will be eagerly doing esterification? Formic acid and not acetic acid. So once this alcohol, the lone pair of electrons of oxygen of alcohol gets attached to this carbon, it will also get protonated. Now this plus will try to neutralize itself and do what? It will do proton transfer, as in this hydrogen, the electron is gained by this oxygen, but it at the same point of time, it is the H plus that will be formed, the proton that will be formed will be exchanged, will be transferred to this OH. There is case of proton transfer, because we know that this oxygen is also having, is eagerly waiting to give its electron. I definitely assure you this, that that's why I have used a reversible sign in whole of the mechanism, because if this can take place, then opposite, I mean this lone pair, now it will snatch electron from this hydrogen and this lone pair will be giving, so I can come back over there. So that's why I'm saying esterification is a reversible reaction and it can be reversed at any point of time. Therefore you always have to remove the excess of the product that is removed. That's why in esterification I have given a reversible sign at every point of time. So it is a highly reversible reaction, but if at all ester is produced, how it is produced, so I am giving you the mechanism. Now post the formation of this OH2 plus, this is water. So this water can be removed if the lone pair, if this oxygen snatches electron from this carbon, it will create a positivity at this carbon and this water molecule will be gone. So if I make some arrangement of removing water from this reaction, the reaction will be proceeding to forward direction. What we have got over here, we have got a protonated ester, and once we have received this protonated ester, the catalyst H plus, the H plus which was given by the catalyst has to be given back. That's why it's a catalyst. So this hydrogen electron is snatched and it is removed in form of H plus. That's why we have given the interest, the udhar, the borrow thing that we have taken from the catalyst, the H plus, it is removed and you get your beautiful ester. Now because many students feel difficulty in giving IUPAC name of this ester, so I have given its IUPAC name also. What is its IUPAC name? Whatever alkyl group is attached to the oxygen, you name it first without any number. You treat it as a branch, but without any number. If in the starting you name an alkyl group, that alkyl group represents the R dash that is connected with oxygen, which is not a main chain, because main chain will be this carbon, because this is this C double bond O is the functional group and numbering will be starting from here. So whatever will be the number of carbon atom, the main chain, it will, the alk will be decided by the length of R and C. That's why I have written alkyl. So this alkyl will be decided by this R dash. If it is CH3, it is methyl. If it is C2H5, it is ethyl. Post that, the main chain R and C will decide the name of alk, because generally we are taking it as saturated main chain. So an ane will come, and because this is the first carbon, so numbering will be 1. And what is the suffix of ester? This double bond O and the single bonded O is termed as O8. So suffix will be O8. Because this is a vowel and E is also a vowel, so this vowel is strike down. So IUPAC name of ester is alkyl alkane O8. I hope we are clear with this. So this ends the reactions of alcohols where O bond H is broken. Moving forward. So this brings us to those reactions where cleavage of, that is breaking of, C bond O bond takes place. Now we very well know, we have done that in the previous slide, that C bond O is a very strong bond, difficult to be broken. So alcohol undergoes this C bond O cleavage only when alcohol undergoes protonation, because after protonation the C bond O can be broken. And one more thing, in the cleavage of O bond H, we have studied the reactions of alcohols and phenols because both of them shows that reaction. But with the cleavage of C bond O, just like in case of alkyl and aryl halides, they were giving different reactions. So now we are not including the reaction of phenols. The other reaction of phenols we'll be reading separately, independently, and here we are only discussing about aliphatic alcohols now. This is the beauty of organic chemistry. The capital A, the first set of reactions where C bond O bond of aliphatic alcohols are broken, they are just the similar reactions that we have read in alkyl and aryl halides. Remember the preparation of alkyl halides. So we can prepare alkyl halide from aliphatic alcohols. How? All those reactions which we have done in alkyl halide, it is important for your class 12 boards also, and obviously JEE also loves them. So I hope we remember these 9 reactions. The first 2 reactions are nothing but the same reaction with concentrated acid. So first protonation take place, and then halogen as X minus gets substituted to the delta positivity of alkyl carbon, that is alkyl group. So this is nothing but SN reaction. Now we also remember that from alkyl and aryl halides, those who have not read it, I highly suggest, it is important for class 12th also, but I'm repeating the basics over here again. SN reactions are basically of 2 types, SN1 and SN2. If backside attack can take place easily when there is no hindrance, as in case of 1 degree, if this alcohol is least hindered, what substitution is generally preferred? SN2. But with 2 degree and 3 degree, we also know this through this chapter now, that this alcohol needs to be get protonated, and once it gets protonated, it can easily form carbocation. But 1 degree carbocation is not stable, it is unstable. So with 1 degree carbocation, it prefers to do SN2, else generally SN1 mechanism is seen. Now, one more famous reagent for this concentrated HX is you use concentrated HCl only in presence of a Lewis acid, which is anhydrous ZnCl2 in the ratio 1:1. This is nothing but Lucas reagent. This process is also termed as Groove's process. It will again be a SN1 mechanism, and therefore which alcohol will be treating to a faster extent? 3 degree alcohol. So 3 degree alcohol will create alkyl chloride, but this alkyl chloride is even visible to our naked eyes. Why? Because it creates a physical presence. Physical presence, how? It creates a white turbidity. So white turbidity is produced instantly because 3 degree carbocation are instantly formed because they are stable. So 3 degree alcohol forms white turbidity instantly. 2 degree alcohol forms white turbidity, but by after heating, and it also forms if you heat it for a span of 4 to 5 minutes, then you get white turbidity. And 1 degree alcohol, because again I'm telling you 1 degree carbocation is not stable, it is actually unstable. But if you vigorously try to do something, like if you heat the mixture, the 1 degree alcohol with Lucas reagent for like 30 minutes, 25 minutes, then it will definitely give you some white turbidity. So the famous Lucas test also we have remembered with this. So these are those set of reactions in which C bond O of alcohol is broken and you are producing alkyl halides. The third set of reaction, that is lab method. With NaBr you get RBr, with NaI you get Ri, but with NaI you can only use H3PO4, because if you use H2SO4, I minus will be oxidized to I2 and no alkyl iodide will be produced. Remember those alkyl halide things, I'm repeating everything. Then phosphorus halides, if I take PX3, I get Rx, whatever halogen I have used, but the byproduct will be H3PO3. Pi3 is not known in nature because P bond I is very large. So rather we create Pi3. How? Using red phosphorus and I2. It also produces Rx, and the byproduct is also that same H3 orthophosphorus acid, which is H3PO3. The pentahalides that is known in nature is just PCl5. So with PCl5 you get alkyl chloride. Again that C bond O is broken, but the byproducts are beautiful over here. It is POCl3 and HCl. This POCl3 is a tetrahedral molecule with respect to phosphorus. The last reactions where C bond O gets broken is with thionyl chloride, but with thionyl chloride also we remember, if you use just SOCl2 and if you use SOCl2 in presence of a base which is pyridine, the mechanism changes. With SOCl2, retention takes place because mechanism becomes substitution nucleophilic intermolecular, and without pyridine, retention takes place, so mechanism is SNI, and with pyridine, the basic conventional SN2 mechanism takes place. We have done these mechanisms in detail in alkyl and arylides, but I'm telling you, for JEE mains, you can, if you just remember this, that in presence of pyridine, in presence of base, SN2 mechanism takes place, and in absence of base, if you just have thionyl chloride, which is SOCl2, SNI will take place, where if this carbon is optically active, then the product will be having a similar optical activity. Let's say if it is dextro, it will also be dextro. But if you use pyridine and if alcohol is dextro, then the product will be a levorotatory product. I hope you remember this. Moving to the capital B set of reaction. So first set of reaction where C bond O is broken, alkyl halides can be formed. So those are the examples. Second set of reaction where C bond O is broken is the reactions where you do dehydration of alcohols. When you do dehydration of alcohol, in that time, during that time also, what bond is broken? C bond O. Now these reactions also we have read in organic chemistry, where in the reactions in the preparation of alkenes. So again, if you have read hydrocarbons, so these reactions we have already seen. Those who have not read hydrocarbon, I'm explaining this again because generally hydrocarbon is a class 11 topic. So class 12 student who want just to read this for boards, I'm repeating everything for you. Now, alcohols generally undergo elimination. How? So let me first give you the mechanism. Generally, alcohol undergoes elimination via even mechanism. Now, what is even mechanism? The full form is unimolecular elimination, which is nothing but a basically a two-step process. We know C bond O of alcohol cannot be broken. In order to break it, I need to protonate that alcohol. So, first step is formation of carbocation. How? Let's say I have this alcohol. This alcohol in presence of an acid gets protonated. Sir, we already know this. So what you get, you form a protonated alcohol. Now this protonated alcohol will try to release water, that is, it will try to dehydrate, which will be the rate determining step, the slowest step. Why? Because it will lead to the formation of carbocation. Now, formation of carbocation, again we have done this in the previous slides also. It will first have an option of ring expansion. After that, it will have an option of rearrangement. Once it has been stabilized to the maximum capacity, now, if there was a nucleophile, then we have done that, substitution will take place. But here we have what reagent we use? We use concentrated sulfuric acid or some dehydrating agent. Now concentrated sulfuric acid will definitely give you H+, which will protonate the alcohol. After that, the conjugate base, which is HSO4- is left. Now in second step, deprotonation will take place to form alkene. How? Whatever conjugate base you have left with, that conjugate base will give electron to the hydrogen of the beta carbon. Now if the hydrogen of the beta carbon is receiving electron from the conjugate base, this HSO4- will take that H and it will be removed as H2SO4, and the electrons of that hydrogen will be given to this carbon. Thereby a double bond will be produced. So dehydration of alcohol produces alkene. Because this is a two-step process in which the first step is the rate determining step. So how many reactants we have in the first step? This is the catalyst. So only one reactant we have utilized. So molecularity of such reactions is 1. Now, because that is the first step is the rate determining step. So from chemical kinetics, how you will write the rate of reaction? Rate of reaction will be directly proportional to concentration of what reactant? Sir, only alcohol. So concentration of alcohol raised to the power 1, this power 1 has been assigned experimentally, and power of concentration term, if you add that power, it is termed as order of the reaction. So this order of the reaction is determined experimentally. So order is 1, molecularity is 1. So for even elimination, order and molecularity both are 1. Now we have read this in alkyl halide, so I'm iterating that for E2 mechanism, order and molecularity both are 2. For even CB mechanism, order of such reactions is 1, but order of such reactions are 2, but molecularity is 1. Remember that even CB mechanism, which generally happens in case of alkyl fluoride. So for that, I highly suggest you should at least revise that alkyl and aryl halides topic. But I hope we are clear till this, that whenever C bond O is broken, then alcohol can undergo dehydration as well, but we need strong dehydrating agent. And what are these dehydrating agents? These dehydrating agents are generally concentrated acid. And which carbocation can be formed easily? 3 degree. So ease of dehydration, reactivity of alcohols towards dehydration will be 3 degree. Alcohol will be dehydrating to the maximum extent. Lesser is 2 degree, and 1 degree alcohol, actually it is a JEE advanced thing, but you should at least know this, because 1 degree carbocation is not stable. It is not at all stable. Therefore 1 degree alcohol also undergoes dehydration, but it undergoes dehydration simply using E2 mechanism, which is beta elimination, the same way as if alkyl halide undergoes elimination to form alkene. So that E2 mechanism will be a one-step process where no carbocation will be formed, hence there will be no rearrangements. So 1 degree alcohol also undergoes dehydration, but via E2 mechanism. Now, how questions will be served to you? That 1 degree alcohol requires excess, because it is not at all loving to undergo dehydration. It is least reactive among all alcohols. So this 1 degree alcohol, when reacted with sulfuric acid, it will be treated at a higher temperature, and that higher temperature will force this alcohol to form alkene. What alkene will be formed? The beta elimination product. So ethanol will give ethene. Let's say if I have this propane 2-ol, so this OH will be gone, and the beta carbon, either you could take this carbon or this carbon, hydrogen will be gone, so this propene will be formed. But because 2 degree alcohol is more reactive towards dehydration, so look at the temperature is reduced, and even it was using H2SO4, concentrated H2SO4. It is using a weaker acid, H3PO4. That too, the concentration of weaker acid is also less. So this is an NCERT fact, which is actually giving you an experiment to tell you and explain you that 1 degree alcohol is least reactive towards dehydration. 2 degrees more reactive, that's why it is using a weaker acid, that too with a lesser concentration, and that too at a lower temperature. And if you take a 3 degree alcohol, I'm using a weaker acid. The concentration is also close to dilute, 20%. The temperature is also quite less, because this shows that 3 degree alcohol will form alkene to a larger extent. Why? Because 3 degree carbocation will be more stable. Now, if you have more than one beta carbon, then beta carbon of which then hydrogen of which beta carbon will be removed, which will give you most stable alkene, because ultimately whatever alkene is produced should be most stable. So the SIDZEF product is also preferred over here. That means that alkene is formed which is more stable. How do you see the stability of alkene? By counting the hyperconjugating hydrogens. Now, for mains, this for your class 12, this is more than sufficient, but for your mains, so if all those students who are reading this for mains, I highly suggest, as I've told in the beginning of the chapter, for organic chemistry, you should always go sequentially. So read hydrocarbons first, then go to alkyl halide, and then come to alcohol phenol ether. It will make a link of concepts which will be required as a couple for a good question of organic chemistry for your JEE mains. Now, moving to, this was the second capital B set of reactions where C bond O is broken. Coming to the next, okay, I've again got this oxidation. Coming to the, okay, so there were only two set of reactions. When C bond O used to be broken for alcohols, what set of reactions we had? Two. What is the first set of reaction? Where alkylides were where alcohols were used to form alkylides, and the second set of reaction is the dehydration of alcohols. Now, there are some reactions of aliphatic alcohols in which both C bond O and O bond H both are broken. I mean, C bond O is also gone, O bond H is also gone. Such reactions are basically of two types again. The first set of such reactions are nothing but oxidation of alcohols. Now, what is if you oxidize an alcohol? What is the next step oxidized product? Either aldehyde or ketone. If you oxidize aldehydes, what is the next step oxidized product? Carboxylic acid. Ketones are generally difficult to oxidize because the action of oxidizing agent is to replace C bond H with C bond OH. We have done that also in hydrocarbons. But again, I'm repeating for all those students who have not read hydrocarbons till now. So basically, oxidizing agent has the capacity to convert C bond H into C bond OH. Oxidizing agent do not have a capacity to break C bond C. Yes, under vigorous condition, you can specially use to break C bond C, but normally oxidizing agent, even strong oxidizing agents, strong oxidizing agent converts all the C bond H to C bond OH. Mild oxidizing agent converts only single C bond H into C bond OH. So for oxidation of alcohols, if I have a 1 degree alcohol, so with this 1 degree alcohol with a mild oxidizing agent, mild will do the C bond H conversion to C bond OH only once. So this single C bond H will be replaced by OH. So if a carbon is having 2 OH, it will undergo dehydration and will form aldehyde. So with mild oxidizing agent, 1 degree alcohol forms aldehyde. But with strong oxidizing agent is not going to leave that carbonyl carbon also. It will also change this C bond H also to OH, resulting in the formation of carboxylic acid. I hope we know this through hydrocarbons also. Now, if I have a 2 degree alcohol, then even if you use mild or you use strong, because it is having only one C bond H, and oxidizing agent do not have a power to break this C bond C. The C bond C can be broken but via vigorous condition, which generally means never ask. So for a 2 degree alcohol, you use even mild or strong oxidizing agent, you land up with only ketones, because ketones are further difficult to be getting oxidized. And going by the same logic, if I have a 3 degree alcohol, then this carbon is not having any C bond H. So either with mild or strong oxidizing agent, it will give you no reaction. Now, practically speaking, the list of oxidizing agents for advance is a complete chapter. So we have to read all those oxidizing agents. Thanks to the mother nature and NTA, no. These are the famous oxidizing agent which your class 12 CBSE board also loves and which JEE mains also loves. What are these? What is this list? Mild oxidizing agent. There are two famous mild oxidizing agents. First is PCC, known as pyridinium chlorochromate, but thanks to NTA in question you will only see the word PCC. Let me clarify what is PCC. PCC is actually a complex compound formed by CrO3, chromium trioxide, pyridine and HCl. They constitute a complex which is termed as pyridinium chlorochromate, generally written as PCC. So if you just remember this PCC, it is more than sufficient. It will act as a mild oxidizing agent. Then if you have this CrO3 but in anhydrous medium, so in question if it is only written CrO3, even if it is not mentioned that medium is anhydrous, still you take it as a mild oxidizing agent, because when this CrO3 is specially added with strong acid, that means medium has to be made acidic. So if CrO3 plus H plus is given or H2SO4 is given, then it turns into a strong oxidizing agent, and this is actually known as Jones reagent. And the other two strong oxidizing agent you already know, K2Cr2O7 in acidic medium, and KMnO4 acts as a strong oxidizing agent in both acidic and basic medium. But in basic medium, if you form acid, then for reporting acid as acid, you have to do acidic hydrolysis, that we'll be doing in carboxylic acids with examples, because those examples are very much loved by JEE Mains. But I hope this is clear to us that these are the famous strong oxidizing agent. One strong oxidizing agent that I'm adding at this point of time is the Jones reagent. So if in the question CrO3 with H plus is given, that means it is a strong oxidizing agent. If only CrO3 is given, that means it's a mild oxidizing agent. Mild oxidizing agent does what? 1 degree alcohol to aldehyde, 2 degree to ketone. Strong does 1 degree to acid and 2 degree to ketone. With 3 degree, no oxidizing agent can do anything. But if you know redox reaction, then through redox reaction we know addition of oxygen is oxidation. Removal of hydrogen is also oxidation, my friends. So if I have a reagent that can remove hydrogen, that can remove only hydrogen, that means that can undergo dehydrogenation of alcohol, then also, although the action is different, but the result will be same. Why? Because if I add oxygen, you will get oxidized. If I remove hydrogen, still you will get oxidized. Just count the number of atoms in the molecule. Let's say I have a 1 degree alcohol and I am telling you it is a very famous dehydrogenating agent, which is copper. Heated copper at around 300 degrees Celsius. In Kelvin, obviously at 273. So it will be 573, but 300 degrees Celsius is easy to remember. So with 1 degree alcohol, you remove hydrogen. Okay, so remove this hydrogen also, remove this hydrogen also. So if you remove hydrogen, what you got? RCHO. That means you got an aldehyde. So such a reaction will restrict aldehyde to not form an acid. So it is better not to use mild oxidizing agent, rather use dehydrogenating agent, which is heated copper. With 2 degree alcohols, you remove one hydrogen and one hydrogen. So after this dehydrogenation, what you get? You get a ketone. And with a 3 degree alcohol, strong oxidizing agent used to do nothing. But this dehydrogenating agent still has a capacity to remove. So what? Instead, this heated copper also has high temperature. So with 3 degree alcohol at this high temperature, this carbocation is formed, and this carbocation once formed will try to form an alkene. So this copper will take hydrogen, because the electron of hydrogen will be given to this carbocation, and it will result in the formation of an alkene. So with 3 degree alcohol also, dehydrogenating agent, which is heated copper, will not give no reaction. It will ultimately give dehydration product, which is an alkene, the product that we get using the dehydrating agent like H3PO4, H2SO4. So these are the reactions of alcohols. Now let us attempt some questions and see to the fact that yes, whatever NCERT offers, that is only asked even in JEE Mains also and advanced also. You will get so many number of questions from the reactions of alcohols that we have seen. You can obviously attempt them through your PYQs and with the sheet attached. I have deliberately taken, although these are also mains question, these is also a mains 2024 question, but with these questions I have deliberately taken such questions, such examples, which will help you to digest the fact that I've told you organic is a subject, is an area which you should always read sequentially. So as I've mentioned previously also, if you want to actually do very great with organic chemistry, learn it sequentially as in GOC1, GOC2, hydrocarbons, alkyl halides, and then alcohols, because now you'll clearly see organic in mains also. For good questions, they make it a packet, but those good questions are also not time requiring questions. They will create an edge for you, so that you who has taken organic chemistry as a sequential subject, so you know everything, and therefore these good questions also you will be able to attempt in a click. Let us practice this now. This is an alcohol, we can clearly see. It is getting reacted with concentrated H2SO4 and heat. Sir, we have already seen this is a dehydrating agent. So dehydrating agent does what? It does dehydration. So post protonation, it will be gone and I'll be getting a carbocation. And then the deprotonation will take place. So if I have a carbocation over here, it is maximum stabilized because even elimination takes place for dehydration of alcohols. So no rearrangement will take place, and you remove any of the beta carbon because this is also a beta carbon, this is also a beta carbon, and both beta carbon will be producing the similar alkene. So what will be the alkene? I'll get a double bond over here. So I guess it is quite clear that this A will be an alkene. So this can be your answer. This can be your answer. No, because this is not more substituted product, and this is also not A because this is not more substituted product. So with A, we have eliminated two options. Now, this is acid chloride in presence of pyridine. So classic case of esterification. We know alcohol and acid and its derivatives undergo esterification and forms corresponding ester. So what will be gone? This hydrogen of alcohol will be gone, and the substituted part. What is the substituted part? C double bond O. Okay, I'm sorry. The substituted part will be just Cl. So you will get this oxygen will be getting this C with double bonded O and then CH3. So yes, this is an ester. So this is right. No, this is showing some substitution. Why substitution will take place? So this is of no, waste. So esterification has taken place. So option A is your right answer. But sir, this question has only required knowledge of alcohols. You were saying it is a packet. Like you will get such questions also where you are required to know more than one reactions of alcohol. So let us attempt this another question from JEE Mains only. This is also a 2024 question, some other shift. Now, what is Jones reagent? Sir, Jones reagent is CrO3 in acidic medium. So it's a strong oxidizing agent. So what does a strong oxidizing agent do? Because it is a 1 degree alcohol. So this alcohol, how many carbon alcohol you have? 2 carbon. So you will get a 2 carbon carboxylic acid because it's a strong oxidizing agent, and 1 degree alcohol converts to corresponding carboxylic acid with a strong oxidizing agent. Rather, if it would have been a 2 degree alcohol, you would have only oxidized till ketone, no matter strong oxidizing agent or mild oxidizing agent. I hope you remember that. Now, this KMnO4 will also help the Jones reagent to actually bring this acid to an acid. So these two will do the same job. So actually you can say that KMnO4 do nothing extra. So this will be the product after Roman number 2 as in second step also. Yeah, industrially speaking, if I'm using more strong oxidizing agent, then percentage yield, that most of the percentage of alcohol will be converted to most of the percentage of, so percentage yield of the reaction will be high. But such things are not asked in the question, although technically speaking this was not even required also, but this is a JEE Mains question, hence discussing. Now I'm telling you that if you just read alcohol chapter, then you can't do this question. Why? Because acid with base, when acid reacts with soda in presence of lime, this lime has no use for the reaction per se. Yes, lime is required for to keep the reaction mixture dry, and this is classic case of soda lime decarboxylation. I hope you remember that, because this sodium when reacts with this base, when reacts with acid, forms corresponding salt, and that sodium salt of carboxylic acid further reacts with this base, and CO2 will be released in the form of Na2CO3. So this CO2 will be gone in the form of Na2CO3 because CO2 is an acidic oxide. It will react with base and forms this. So decarboxylation will take place, and this CH3 will be getting the hydrogen. So your product will be actually, the organic compound that you'll be getting is methane. This is soda lime decarboxylation, a topic from hydrocarbons. So once you know organic sequentially, only then you will be knowing that your answer will be option number A, methane. Again, now for doing such questions, you need to learn alkyl halides also. Why, sir? This is alcohol. It is reacting with sir, phosphorus halides. It was there in alcohol also, we have seen, so we know. But yes, it is there in alkyl halide also. So C bond O will be broken and you will be getting the corresponding, I mean everything is same, just this OH is removed and you have got a bromine. So this is a classic SN2 substitution where OH is substituted by phosphorus halides. Byproduct will be H3PO3 for phosphorus acid, but that is not asked. Now with this alcoholic KOH, sir, alcoholic KOH with alkyl halide does what? It does beta elimination. It does E2 elimination, beta elimination. Now this you have learned in alkyl halides. So sir, beta elimination do what? It creates an alkene. But what alkene? More stable alkene. More stable alkene is the major product, and when it is more substituted, it is called Sidzev product. Else it, even if it is less substituted, but still if it becomes the major product, it is called a Hoffman product. And over here both these carbon have same number of hydrogen, so substitution is same. But if you get an alkene over here, it will be pi sigma pi. So because we are forming a conjugated alkene, so it will be more stable. So what will be our major product? This cyclic ring having double bond O here, and will be forming a pi cloud which is in conjugation with this pi cloud. So it's a conjugated alkene which is more stable. So this will be the more stable product. And always when you do elimination, what product you create? More stable product. So let us find this product over here. Yeah, this is a conjugated alkene. So option C will be your right answer. Let us check this option. Yeah, option C is your right answer. So I hope we are clear till this. Now moving to the reaction of phenols. Now C bond O of alcohol breaks like C bond X of alkyl halide breaks, but C bond O of phenol do not break because of the resonance. So first point over here is, now I have already beautifully made this slides for you, so that take them as your class notes. Do not bother to write them. Yes, bother to remember and learn this again and again. If required, make a 2x speed and read these theory 2 times with me. So watch this video twice, or else watching one time properly is also more than sufficient. But always keep on turning these notes. So download these notes, get a printout, and start looking at these notes every morning. If at all you are not comfortable in remembering the theory for a longer duration of time, only for those students I am advising. Now we have already discussed that C bond of phenol is resonance stabilized, so it will not show those reactions like that of alcohols. Point number 1. Point number 2, the O bond H of, when connected to benzene, that is when phenol is formed, this phenol is not electron rich. This OH is a very strong electron donating group. So electron donating group does what? Electron donating group increases electron density. So it increases electron density where? Sir, resonance is always operational at ortho and para position. Now my point is, this is a plus R group, but this plus R group is so activating, so much of electron density is created that, sir, but we cannot see electron. That's what I'm saying. So much of electron density is created that generally for electrophilic substitution reactions, what we need a electrophile, a plus. That plus is always created using another species which can forcefully create an electrophile. Like during nitration, let us talk about the very first example of electrophilic substitution, nitration. Nitration requires what reagent? Concentrated H2SO4 in presence of concentrated HNO3. Although reaction is done by concentrated HNO3, but concentrated HNO3 is forced to produce NO2+. How it is forced? Because H2SO4 is strong acid, so it will be giving H plus and forcing the nitric acid to give OH minus, and then forcefully NO2 plus, the nitro NO2 plus, the nitro NO2 plus is the nitro group, and that nitro group is produced as an electrophile forcefully. But sir, if phenol is very activating, then don't you feel that NO2 plus will be formed by itself? Why? Because that plus will be so much welcomed by the high electron density of this minus that the HNO3 will not even bother to produce NO2 plus, because that NO2 plus is getting so much attraction from the highly activated ring, highly activated benzene ring. And why this benzene ring is highly activated with electrons? Because now these examples show that the plus R effect of phenol of OH is not large, it is very very large. Now sir, but show us the examples. Now see the example. Leave about taking H2SO4 as a catalyst, even if you use HNO3, that too not concentrated, even if you use dilute HNO3, still NO2 plus will be created because this is highly activating group. I hope we are clear what I'm trying to tell you. So even dilute HNO3, when sees phenol, it itself produces NO2 plus, but because it is dilute, so concentration of HNO3 is very less. So limited number of NO2 plus will be created, and they will be going at ortho and para position. Sir, but generally we always write para is the major product, not ortho, but here you have written both the products. Actually, mixture of product is produced because both are produced in very sufficient amount. So here I'm not mentioning which is major, which is minor. Sir, why? Because again, we have discussed in the previous slides, the orthonitrophenol is having intramolecular hydrogen bonding, and because it is for having intramolecular hydrogen bonding, so this guy is not feeling steric hindrance, it is feeling stability. Point number one. Point number two, because it is involved in intramolecular hydrogen bonding, so one ortho molecule and another ortho molecule will not have so much attraction towards each other because they are attracting within themselves. That means if two molecules are having less intermolecular force of attraction, their boiling point will be quite less. If boiling point is less, they can easily get vaporized. So they are highly volatile. Who is highly volatile? The orthoisomer. While the para isomer will be having intermolecular hydrogen bonding, so it will be having a high boiling point and it will be having less volatility. We have again seen in these questions for ortho and para isomers. So these ortho and para isomers are separated via steam distillation. This is another point that we have seen questions also from mains. I hope we are clear till this now. Leave taking H2SO4. Even if we take HNO3, but this time we have taken concentrated HNO3. So if we take concentrated HNO3, then concentration of NO2 plus also will be very large. You do not even stop thinking about taking concentrated H2SO4 because that is not even needed, because NO2 plus will be itself HNO3 will be getting self ionization and forming NO2 plus, because that NO2 plus is in love with the electron rich benzene ring, because this electron richness has been gifted by the strong plus R of the OH group. I have repeated this several number of times. Please do remember this. This is very important. Now, because we have used concentrated HNO3, so NO2 plus concentration will also be large, so it will be going in all the possible places which it can acquire. So it will acquire all the possible cases, and therefore you will be getting picric acid. Now picric acid is industrially a very important compound. All the compounds which have more number of nitrogens are actually used as explosives. So in that industry, picric acid has got a huge industrial use. So now giving an industrial fact to you. Actually, you can make picric acid like this, but industrially the percentage yield of getting picric acid with this path is very less. Why? Because this concentrated HNO3, apart from being doing the function that it is doing over here, that is creating NO2 plus, it is also a strong oxidizing agent, and this oxidizing agent actually oxidizes this phenol. So some percentage of this phenol is oxidized, and what is formed? This is para-benzoquinone. So because concentrated HNO3 is also very strong oxidizing agent, so some percentage of phenol is converted to this quinone form, and some percentage is converted to this picric acid. So industrially speaking, percentage yield of this path is not good. But for your JEE questions, if you are given such reagent, then you will definitely tick such products as your answer, because that will be the percentage, will be, this will be the major product. But let's say it is 52%, for example, I'm telling you. So industrially getting 52% of product and 48% of that thing which you cannot sell is not good. So I want even more than more percentage of product. If I'm investing my whole energy and my life, my industry is dependent upon them. So industrially you should know that this is not how picric acid is produced. Industrially, first you react this phenol with oleum. Now what is oleum? Fuming sulfuric acid, which is mixture of H2SO4 and SO3. Now that free SO3 is behaving as an electrophile, and it will lead to the formation of sulfonic acid. But now we also know, again, because this is a strong plus R group, so it will be creating electron density to a larger extent. So sulfonic acid group will also be trying to getting added to a larger extent. But now this is a fact that all the three places are not acquired by the electrophile SO3. Why? Because sulfur is quite large also. Sulfur is not a second period element, it is a third period element. So at ortho position, if one sulfonic acid group has been created, then it will not be created in another ortho position because of the steric crowding. So it will also get extensively sulfonated, but less extensive sulfonation is occurring because of the fact that sulfur is not second period element, it is quite bulky. So at ortho position there will be only mono ortho substitution, there will be a para substitution because now space has been provided, but the another ortho position will not be acquired. So this is just a practical fact that you have to learn. Now again we are telling this that sulfur is not a second period element. That means the C bond S, the carbon bond sulfur bond length, is very high. So this sulfonic acid group is a very easy leaving group. So once this di-substituted sulfonic acid is treated with concentrated HNO3, now because this is a easy leaving group, so it will leave and now it will make space for the incoming electrophile, which because of HNO3 it will be NO2 plus, and now NO2 plus will be getting into all the possible ortho and para position. So going with this way, I am limiting the use of concentrated HNO3. So because I have limited the use of concentrated HNO3, because concentrated HNO3 is not present alone, it is present with H2SO4, and in presence of H2SO4 it only produces NO2 plus. Hence, because it is producing NO2 plus and not remaining as HNO3, so it can't act as oxidizing agent, so percentage yield of getting picric acid increases. Now for good questions, I'm telling you this. For mains level of questions, I mean, you can leave this part. This the another pathway where it is getting reacted with oleum and then forming picric acid. You can leave this part if you are feeling that sir thoda zyada ho raha hai. So you can leave this part. I'm telling you that. Now, second example of electrophilic substitution is halogenation. Now always remember, phenol, what is the famous example for halogenation? Sir, bromination and chlorination. My friends, phenols only undergo bromination, they do not undergo chlorination. First, I'm telling you that. Now, why not chlorination? Because again, it is a fact that Cl2 also act as an oxidizing agent. So Cl2 also because it acts as an oxidizing agent, so it will oxidize phenol and it is converted to benzoquinone. So for halogenation, always keep this thing in mind that we always do bromination. Rest all the things are same because it is a highly strong activating group, so I do not even need a Lewis acid. Br2 will be self-ionized, forming Br plus and Br minus, because Br plus is in love with this activated ring. So even if I use Br2, leave using Lewis acid because it will undergo self-ionization. Even if you use a non-polar solvent, even if you decrease the temperature to 0 degrees Celsius, still, because this is so much activated ring, still in these conditions also Br plus and Br minus will be formed. Bromine will undergo self ionization, and Br plus, the electrophile, will be getting added at ortho and para position. But over here, obviously, because I have restricted the medium to such an extent, so percentage of Br plus, the electrophile created will be, concentration will be less, so you will get a mono substituted product. And over here, obviously, para will be the major product because there is no intramolecular hydrogen bonding. So generally para isomer is the major product, and over here para is only the major product. And but if I use bromine, leave about using Lewis acid. Lewis acid though you do not even require. Even if you use water, so now medium is polar, so Br plus Br minus will be dissociating to a larger extent. Even water is a universal solvent, very polar in nature. Even if you use organic polar solvent like acetic acid, so you use any polar solvent, do not use Lewis acid. Even if polar solvent is present, then bromine will, Br2 will undergo ionization to a larger extent. So more number of Br plus will be created and it will be extensively substituted. So you will be getting 1, 2, 3, 4, 5, 6, as in 2, 4, 6 tribromophenol. And because this 2-bromo-6 tribromophenol is having 3 bromines, so molecular mass is large, and such compounds are actually not soluble. They get precipitated, and you can see this precipitated. This precipitated is a white PPT. So some people also consider it as a test of phenol, because what all the reactions are not chemical test. What all reactions are considered as a test? All those reactions are considered as a test who gives a physical detection of their getting happened. So if I visually can see white PPT, then I can say yes, definitely if white PPT is formed, then it will be definitely phenol, because Br2 in water forming white PPT is only possible with phenol. So it is also a test of phenol. Now moving to the next very important reactions of phenol, which is the coal-base reaction. Now, as I've already told you, OH is a highly activating group, but icing on the cake, if that phenol forms phenoxide ion. So I am telling you that phenoxide ion is even more electron donating. Why? Because phenol resonating structure will have, ultimately when oxygen will give electron, it will gain a positive charge. We have drawn in the previous slides. If phenoxide ion gives electron through plus R, oxygen is not even getting positive charge, it is becoming neutral. So, and if I'm having excess of electron, I will become an even more stronger donor. So this phenoxide ion is a more strong electron donating group, point number 1, sir. So what we'll do now, this was employed to form some very famous industrial compounds. Now if I use phenol, and because I know phenol is a strong acid than water, so it can react with a base, and it will form a salt, which is sodium phenoxide. Now we know that this phenoxide ion is highly activating, so it will activate the ring at ortho and para position. Now because it is highly activating, the minus that is created over here is even larger in magnitude than a simple phenol. And because this minus is larger, so now even a neutral, even a weak electrophile can be attacked. As in, if you use CO2, now there is no positive charge in CO2. I mean, there is no complete plus, it's a neutral molecule. But we know there is delta positivity. Carbon has a +4 oxidation state, although this is a partial charge. So even this partial charge will make it a electrophile. We definitely know that CO2 is not a charged electrophile, it is a weak electrophile. But because ring is so much activated, because phenoxide ion is so strong activating group, that it can even react with a weak electrophile. Industrially speaking, this reaction takes place at some elevated temperature of 400 Kelvin. Some pressure also you have to apply, around 6 atm pressure. But even if question is not mentioning these temperature and pressure, still you will make the reaction of CO2, because we have, that's why I'm emphasizing on the fact that phenoxide is even a strong activating group than phenol. So it will invite this CO2. Where it will invite? At ortho and para position both. But sir, here you have only drawn the ortho isomer. Why? Because this ortho isomer will again be resonance stabilized, so ortho product becomes the major product. Now this, when this minus is attacked by this carbon, you get carboxyl. This CO2 as in carboxylic acid group is introduced at ortho position, sir, but this is not acid. You have reported a salt because medium is still basic. So acid plus base forms salt. So I have reported sodium salt of carboxylic acid. What is, and post acidification you get your corresponding carboxylic acid. Now this ortho substituted carboxylic acid becomes the major product. Why? Because it is involved in intramolecular hydrogen bonding, hence para is not the major product. And this compound, although its IUPAC name will be 2-hydroxybenzoic acid, but its general name is very famous. This is a very famous industrial compound and known as, its general name is salicylic acid. And this reaction is a naming reaction, very very important reaction of Kolbe's reaction. Now if at all JEE is supplying you this question, then you should just know this much only, that phenol, first it reacts with in presence of NaOH, it will become sodium phenoxide and reacts with CO2, no temperature pressure I am mentioning, followed by acidification, you will form your beautiful salicylic acid. But you can leave this, I mean this is one step moving forward, but for good questions for mains also you should know. Now let me, I mean this is no rocket science. Every detail I've already mentioned, but still, because I'm giving you these notes and they can help you for advanced questions, so I'm moving a bit one step more for this Kolbe reaction. Now this phenoxide ion, we know it is resonance, it is having more plus R, because see, when this minus is gone to the ring, this oxygen is neutral, it is not having any positive charge, and minus is coming to this carbon. Okay, so this carbon will be a better donor because oxygen is electronegative, this carbon is electropositive, so it will donate. It will donate to what? It will donate to the carbon. This carbon is not having a complete plus, so it's a weak electrolyte. But because the electron density has been increased to a much larger extent, so even this minus can attack this electrophile. Once it is attacked, the carbon gets substituted and you get such a structure. Now because here aromaticity is lost, so in order to regain aromaticity, the substitution will take place. That means deprotonation, hydrogen electron is taken and this extra electron will be taken by this oxygen. So you get, after deprotonation, you get the regain of aromaticity. So this aromaticity is regained. This becomes single bond O. Now once this H was released in form of H plus and this oxygen has attained the extra minus, so this minus and this plus will be forming this OH bond. So in the reaction, the hydrogen that is coming to phenol is coming from where? Is coming from the benzene ring. The hydrogen of benzene ring is actually going to this phenol. This becomes minus, that means this produces the sodium salt of salicylic acid, and post acidification, the hydrogen that is coming to carboxylic acid is, after the acidification, this green hydrogen is actually going to salicylic acid. So for good questions, if isotopic effect is thalcophyte in the question, then you know oxygen is getting hydrogen of benzene ring and acidification is giving the hydrogen to carboxylic acid. So I hope you know, you have understood this point. Now one more extra point I'm trying to tell you. Sir, you said orthoisomer is more stable because it is involved in intramolecular hydrogen bonding, so it will always be the major product. No, although a step moving one step more from mains, so this but I'm telling you, it is a good for good questions it is important. If you increase the temperature by what? Remember, till 400 Kelvin you are allowed to form orthoisomer, but if you increase the temperature and exceed by a value of 430 Kelvin, so above 430 Kelvin, now para isomer becomes the major product, because now steric hindrance will start coming into play. So now para will become the major product. So then salicylic acid will not be produced. Major product will be para isomer. Now also para isomer will be formed. Over here we have used sodium salt of carboxylic sodium phenoxide. If you use potassium phenoxide, so instead of NaOH, if I use KOH, then also para isomer will become the major product. Now third thing is, sir, inorganically can we produce CO2? Yes. So even if you use CCl4, which is a non-polar solvent, in presence of base like KOH and NaOH and heat, that means this CCl4 will react with KOH and ultimately it will form CO2. So even if you use CCl4, not chloroform, because initially I have used CO2. So even if I use CCl4, this CCl4 will ultimately form CO2, and that's CO2 will form both the ortho and para isomer. But over here, I'm not mentioning salicylic acid. I'm mentioning both ortho and para isomer is produced, because you can clearly see I'm using KOH. Yes, if you use NOH, then orthoisomer will become the major product. So that's why, because I'm using KOH, I am deliberately writing both ortho and para isomer, because now I'm telling you this is for good questions. But if I use NOH, then you can definitely form ortho isomer will be the major product. So these are some extra points regarding coal-based reaction. Coming to the next important reaction of phenols, which is Remertimal reaction. It is approximately the same logic. Phenol, a highly activating group, in presence of base, it will form phenoxide. But now, instead of CO2, what I have? Chloroform. Now, if this chloroform, how this chloroform gets attached? Again, it can get attached at ortho also, para also, but here also ortho becomes the major product because of the similar fact, which is orthoisomer here also is more stable because of intramolecular hydrogen bonding. Sir, but what is the electrophile? So coming to the mechanism directly, because knowing the electrophile is very, very important here. This is chloroform. I can definitely see because of -I of 3 chlorine. This carbon is also acidic. So this acidic carbon will do what? Sir, this acidic carbon, what does acid do? Acid gains electron. So it will snatch away the electron of hydrogen, but this can only happen in presence of a base. That's why we have used NaOH. So this base will give electron, and electron will be given to this hydrogen. This hydrogen is gone in the form of H+. So water, H2O, is dehydration takes place, and you get a carbon ion. Now this carbon is having this minus sign, minus charge, but it is not having the capability. Carbon is not electronegative. It is becoming electronegative because 3 chlorine are demanding electron from this carbon. And as soon as this carbon has received extra electron, the extra electron will be snatched by one of the chlorine and will be removed as Cl minus. So what you are left with? This carbon, the 2 chlorines, but this carbon will be having a lone pair. Having lone pair does not mean it is electron rich. Carbon is having how many electrons in its valence shell? 4. The extra electron that carbon has taken is gone. How many bonds it is making? Out of those 4 valence electrons of carbon, how many bonds it is making? 2 bonds with whom? Chlorine here also, applying their -I. So out of my 4 electrons, 2 are forming bonds. So 2 forming 2 bonds. So there are 4 valence electrons I have got through the bonding also. And as an isolated species, I was having how many electrons? 4. So 1, 2 have formed a covalent bond, but I will be left with my 2 electrons. So 1, 2 forming bonds, 2, 1, 2, 3, 4, 5, 6. So this carbon, the extra lone pair is not the extra electron. It is still having 6 valence electron. That means it is still electron deficient. That's why I was emphasizing on the chemical bonding of this carbon. So this dichlorocarbene is ultimately having 6 valence electron, not 8. So this lone pair is not excess of electron. It still is deficient of 2 electrons. So it is the electrophile. And electrophile will be attacked by whom? By the ortho and para position of benzene ring. Not benzene ring, of the phenoxide ion, because over here also medium is basic. So this is also a strong electron donating group, because phenoxide is strong electron donating group. So here also this is also neutral. So this minus will be attacking this carbon, and this carbon will be getting attached. But this carbon has gained extra electron, so it will attain a minus charge. Again, deprotonation will take place, and this hydrogen will be removed in the form of H+. But now oxygen will also get minus, carbon will also get minus. Who is more electronegative? Oxygen. So who will now give electron to hydrogen? This carbon. So this minus will give electron to hydrogen. So now the hydrogen that has been substituted by benzene ring is not going to oxygen. It is going actually to the carbon that is getting attached. And now because medium is basic and it is having 2 chlorine, so this is a benzylic carbon. SN1 substitution will take place, chlorine will be removed and OH will be formed because medium is still basic. So this is a concept of alkyl and aryl halides, chlorine undergoing SN substitution reaction in basic medium, NaOH aqueous, KOH aqueous. So these two OH we already know. Vicinal diols, vicinal as in one, the similar carbon is having 2 OH is unstable because oxygen are highly electronegative. So in order to stabilize, what happens? Dehydration takes place. So what is dehydration? H2O. So remove this water molecule. So this oxygen will become a double bonded oxygen. So post dehydration, what have you formed? Sir, we formed an aldehyde. But this aldehyde is also having a minus over here because this oxygen is still having the minus sign because medium is still basic. So it is still in the form of phenoxide ion. So post acidification, this O minus is also getting H plus, and why? Again, I have made the orthoisomer because it is involved in intramolecular hydrogen bonding, and this product is known as salicylaldehyde. In coal-base reaction, what we formed is salicylic acid. Over here in Remertiman reaction, what we are forming? Salicylaldehyde. So these are very famous 2 reactions of phenols. Moving to the last reaction of phenol, which is oxidation and reduction of phenol. Now this is quite simple. In order to reduce phenol, although it is difficult, but yes, it can be done using zinc dust. It is a highly specific reaction. If you use zinc in presence of heat, this oxygen is removed in the form of zinc oxide and the hydrogen gets substituted to the ring. So you get a reduced product of benzene. A very famous question, a very famous reactions essentially of directly from NCERT. Now, although difficult because this is stable, but still you can destabilize this benzene ring of phenol by oxidizing it. Not easy to do, but it can be oxidized using chromic acid. What is chromic acid? Chromic acid is formed, it is actually a salt which is Na2Cr2O7 in acidic medium. The acidic medium is generally created using sulfuric acid. So this mixture is actually known as chromic acid. And what does the strong oxidizing agent do? It even crashes the aromaticity of benzene ring and result in the formation of benzoquinone. But this benzoquinone, when getting oxidized, has a property also. So it's a test. Not normally, but when this benzoquinone is kept in air. So whenever this reaction is taking place in air, you can see the product produced. Why? Because this is walking one step extra, but this knowledge is there in NCERT. Actually, what happens is in air, this quinone exists as a dark colored mixture which you can see. So that becomes a test also. And if somebody asks you why it is showing that dark color, because of a complex formation. That complex formation is due to the intermolecular hydrogen bonding, not intra. This is your benzoquinone. In presence of air, this benzoquinone exists as a complex, as a mixture of this quinone, hydrogen bonding is between this O and the hydrogen of phenol. So this is hydrogen bonding with 2 units of phenol, and this composition is actually making the solution look a very brilliant red in color. So you can see that solution, and if you see that brilliant redness, then this also some people treat it as a test of phenol. So this oxidation, okay, after this I will come to this commercially I'll come to that commercially important alcohol later, but because we are discussing about test, reactions of phenols are done. But after the reactions of phenols are done, let me quickly summarize this thing for you, that there are some very important tests which we have already seen, but let us summarize those tests. What is a test? Where a reaction taking place, and if you can see those reactions, then that reactions can be termed as a test. So the first test is Lucas test. We have done, I guess, in this alcohol also. I've explained it twice, and we have done that in alkyl halide. So with 1 degree, you get no PPT. After 30 minutes, white turbidity. With 2 degree, after 4 to 5 minutes on heating, with 3 degree, you get immediate white PPT. So this is distinction between 1 degree, 2 degree, 3 degree alcohol via Lucas test. Second is Victor-Mayer test. Now, what is Victor-Mayer reagent? You can skip that also, but at least you should remember this. That remember it with a rhyme. Rhyme is RBC. You know, red blood cells. So remember it with a line RBC. Now, 1 degree alcohol gives red color with Victor-Mayer reagent. 2 degree gives blue color, and 3 degree do not give any color, so it remains colorless. Now, what is Victor-Mayer reagent? It is actually a sequence of reaction. You can leave this if you are learning it for the first time and your boards are very close, so you can leave this, but for good questions you should know this. What is this Victor-Mayer reagent? First, you react alcohol with red phosphorus I2. That means you are replacing this OH with iodine. Then you treat it with AgNO2 silver nitrite. Then you replace this iodine by NO2 nitro group. Then you react it with nitrous acid. Nitrous acid is unstable. You do not get its bottle. So how you will make the reaction with nitrous acid? Using a mixture of NaNO2 and HCl, and followed by reaction with base. Use any base, NaOH or KOH. You will get your color. Now the reaction I'm not even giving you, but at least for good question you should just know the sequence, that what is the sequence of reagent used by Victor-Mayer. So this sequential reactions becomes your Victor-Mayer reagent. So 1 degree alcohol gives red color, R, blue, C. So 1 degree, 2 degree, 3 degree, you can make a distinction using Victor-Mayer test also. Now, next is the effervescence test, which is actually used to distinguish between phenol and benzoic acid, because phenol is a stronger acid than water, so it reacts with base, but phenol is not stronger than carbonic acid, H2CO3. So carboxylic acid is even stronger than H2CO3, carbonic acid. So when benzoic acid is treated with, or any carboxylic acid is treated with sodium bicarbonate or carbonate salt, they can react because carbonic acid is a weaker acid than any carboxylic acid. Carboxylic acid are stronger, so they will undergo neutralization and you will form a sodium salt of corresponding carboxylic acid, H2O, and CO2 will be released. Because CO2 is getting released because of formation of H2CO3, because H2CO3 is weak also than carboxylic acid, and it is an unstable acid. So H2CO3 whenever form H2O and CO2, and whenever CO2 is produced, you can hear those CO2 molecules releasing. Why? Because it creates brisk effervescence. That brisk effervescence confirms the presence of release of CO2. So this effervescence test is given by carboxylic acid, but they will not be given by phenol, because phenol is a weaker acid than H2CO3, so it will not create any brisk effervescence. This is how you distinguish between an acid and a phenol. Obviously, alcohol do not react with base only, so they will definitely not react with bicarbonate. Now, for phenol, there is also one very important test, which is neutral FeCl3. Actually, with FeCl3, phenol forms a complex which you can see. It is a brilliant violet colored complex, and this is because of the formation of this Fe in +3 state and this phenoxide ion. So it forms FeOH whole thrice. So this complex gives a very brilliant color, a violet color, and this violet coloration confirms the presence of phenol. It is only given by phenol, not by aliphatic alcohols. So this is a characteristic test for phenol. And obviously this one we have already seen, that when phenol is treated with bromine in polar solvent, so excessive bromination will take place and you can see this white PPT. So this also becomes one of the tests of phenol. Let us do this one more test of phenols, although it's there in NCERT, but in the chapter of amines, and because it is so much loved by JEE, so because it is a test of phenol, so I'm explaining here only. So there is a compound, we already know it, the famous benzene diazonium salt. Now it can also behave as an electrophile, because we very well see the deficiency of electron in the nitrogen, the positivity in nitrogen. Now this positivity can also be attracted by phenol. Why? Because the OH is still very activating group. So at ortho and para position there will be much of electron density, but because this is a whole ring, so the substitution takes place at para position, because there will be no steric hindrance, and because of this there will be formation of a coupled product. Why I'm saying coupled product, because the N double bond N, the diazo group, is still remained in the product, and such reactions are called coupling reactions. And this para hydroxy azobenzene that is formed, you can also see this because it's a beautiful orange color dye. So this becomes a dye test for phenol. It is also having a huge of importance industrially, because these dyes are actually used as a coloring agent in industry. So if you need to color something orange, then this orange dye is made into application and use. So an important industrial reaction, also a dye test, also why test, because obviously phenol detection can be done when orange color is appearing. So moving to although because it is there in NCERT, and there was a topic from NCERT which was there in board syllabus, also in JEE syllabus also, that is chemistry in everyday life. So there are two very famous alcohols, obviously the methyl alcohol, the very smallest alcohol, methanol, and ethanol. So because methanol and ethanol are the simplest alcohols, but they find huge importance in our daily life. So let us, NCERT devotes a complete page for them. So I'm separately discussing these commercially important alcohol, first being the methyl alcohol, or simply methanol. It is also termed as wood spirit. Now why? Because actually methyl alcohol can also be produced by destructive distillation of wood. What is destructive distillation? When you heat wood, but you try to heat it in absence of air. So absence of heating is termed as destructive distillation, and through that, not because of that, through that you can prepare methyl alcohol. That's why through wood it is created, so it is also called wood spirit. But methyl alcohol, industrially, largely methyl alcohol is produced by the mixture called water gas. This is an inorganic gas which is nothing but mixture of carbon monoxide and hydrogen. Because this water gas is used in the synthesis of, along with methanol, various other organic compounds. So this water gas is also termed as synthesis gas, or simply syn gas, which now why industrially this is very important, very famous, because this water gas you can prepare very easily. Why very easily? Because the raw material is very cheap. You can get methane by combustion of any fossil fuel, by combustion of any organic compound. Generally methane can be easily obtained. So this methane, when subjected to steam, actually produces water gas, and this water gas is taken as a reactant. But this water gas is treated with a mixture of catalyst of zinc oxide and chromium oxide, so ZnO or Cr2O3. But it is a highly specific reaction. It takes place at a temperature of around 300 to 400 degrees Celsius, and at a high pressure of about 200 to 300 atmospheric pressure. When subjected under that condition, the water gas converts itself into methanol. Now why producing methanol industrially is very important? Because obviously because of the huge importance of methanol. So firstly I'm discussing about the use. It is widely used as a solvent. So in industry, what solvent we use for dissolving organic compound? Water cannot be used as a solvent. So actually methanol is used as a solvent in paint industry, in varnishes, and also for the formation of formaldehyde, which is also an industrial the formaldehyde is also industrially well known compound which is having application in large number of industries. So that formaldehyde also you can produce using methanol. How it can be produced? By treating methanol with a catalytic mixture of iron and molybdenum, FeMO catalyst. Under the influence of this catalytic mixture, when you heat methanol, it gets oxidized to form formaldehyde. Now, apart from that, methanol is a colorless liquid. Do remember that. Its boiling point is obviously very much lesser than water. It is around 64 degrees Celsius. This methanol is highly poisonous. It is not the alcohol which is consumed in daily life, because if you drink methanol, you will die. Obviously, with a above a specific concentration, it is so much poisonous that it can even cause death. So coming to the more drinkable alcohol, which is the ethyl alcohol. And yes, ethyl alcohol is the alcohol which is loved by the society also, and has got industrial application also. So let us see how this is prepared. So this ethyl alcohol is basically produced by the process of fermentation. Now, what is this fermentation? Actually, you get, what is sugar? You get various forms of sugar. The source of sugar can be everything, but ultimately, if you have got that disaccharide, the sucrose, which is C12H22O11, which is nothing but a sugar carbohydrate, when you hydrolyze this disaccharide, but this hydrolysis normally it does not take place. It takes place under influence of an enzyme. The name of the enzyme is invertase. It converts sucrose into glucose and fructose, and both these glucose and fructose having the similar molecular formula C6H12O6 under the influence of another enzyme called zymase. Now this zymase enzyme is secreted by a microorganism called yeast. Yeast develop that zymase. So if you need to get this zymase enzyme, then you need to palify the microorganism known as yeast, because yeast secrete this zymase. Now, this process takes place without any air. Remember this, there should be no air. So if you are making a reaction in absence of air, technically speaking, it's an anaerobic condition. So under anaerobic condition, the glucose and fructose by the action of zymase converts themselves into the beautiful ethanol, and CO2 gases released. Now, if this is the alcohol that is consumed in the society also. So some people drink ethanol, some people drink wine. Now what is this wine? In wine making also, the chemically reaction is same, but this sugar, instead of this sugar, what you use, sir, fruits also has got sugar in them. So whenever you have grapes, but what grapes? Grapes that have already ripened. So these grapes already have, when normally grapes do not have very high sugar content. Once the grape gets ripened, after getting ripened, the concentration, the percentage of sugar in them increases drastically. So this sugar, now you have got, now what you do, these grapes undergo self fermentation. But obviously, if you want them to so why they undergo self fermentation? Well, we do not need this zymase, we need this zymase. This zymase actually, when the grapes get ripened, so the yeast start developing on the outer skin of the grapes. So you just crush them and mix water in them. So introduced water, as in you are doing hydrolysis, and after hydrolysis you will obviously the sugar content will be hydrolyzed into monosaccharides, which is glucose and fructose. Yeast, which is already developed in their outer skin, if you crush that, zymase will be introduced with the monosaccharides, the glucose and fructose, and automatically, that's why I'm saying self fermentation, and automatically they turn into ethanol. So but through that process of fermentation, as in when self fermentation of ripened grapes takes place, whatever ethanol we get, that ethanol is actually termed as your wine. So that is why I'm using the term self fermentation. So moving forward, now the enzyme action is inhibited once the percentage of alcohol formed reaches or exceeds a value of 14%. Why? Because this reaction, that is the formation of ethanol from monosaccharides, it is highly reversible. The reaction stops. So whenever 14% of ethanol is produced, because that is the value that is allowed as per the value of equilibrium constant K. Moreover, you can't limit the air to enter any place, because you do not make this reaction in a vacuum, because that will be very, very expensive. So in order to avoid that, no air should get inside the mixture, else if at all this ethanol under the influence of zymase is introduced with air, then oxidation of ethanol takes place. And when ethanol get oxidized, what it is formed, sir, it will produce 2 carbon carboxylic acid, which is nothing but acetic acid, the acid which is there in vinegar. It is khatta, so the taste of the wine will become sour. So because if any of the oxidation takes place, the alcohol taste will get destroyed, therefore it can't be sold in the market. Therefore what we do is, as soon as 14% of alcohol is formed, we have definitely limited the supply of air. We are trying to do this reaction in a perfect anaerobic condition, but nothing is perfect. So whenever 14% alcohol is formed, we kill this zymase, so that the zymase may not be further converting any of the produced ethanol into acetic acid. Now, coming to the properties of ethanol, it, like methanol, it is also colorless liquid, but its boiling point is a bit larger. That was 64, so this is 78 degrees Celsius, but much lesser than water. This ethanol also has got various industrial use. So in industry, if they give you ethanol for working, maybe the workers will drink and they will party. So when ethanol is used industrially, the ethanol is actually denatured. What does denaturation of ethanol mean? We mix it with some substances, like we add copper sulfate. When we have to use ethanol industrially, that means not for drinking purpose, but in order to avoid people from drinking it, we do the process of denaturation. That is, we add copper sulfate into it. Now what copper sulfate do? Copper sulfate, because of its blue color, when added to ethanol, changes the color of the actual ethanol, so people can't recognize that that is ethanol, so they can't drink it. And we also mix it with pyridine, because pyridine has a very foul smelling substance, has a very foul smell. So if you want to drink after change of color also, but if it is smelling like a very foul smell is coming out of it, then there will be less chance that you will be drinking that alcohol. So that ethanol can only be used for industrial purpose. Therefore the alcohol when used industrially, this ethanol when used industrially, is generally denatured. Now this is all about alcohols so alcohols that we should know. Now we are directly moving to the topic of ethers, but before that, let us do some questions. But for questions, I'm again telling you, you should always try and do more, and first read this theory. If at all you do not remember this theory in one go, obviously if you are reading it for the very first time, you will not be able to memorize everything, so you need revision. So if you read revision, make a 2x speed and then read it, and then go for more and more number of questions. Some questions, what questions are preferably at this point of time with limited time, you should always go for your PYQs, the exact question of JEE mains that you are going to attempt in your April examination. So discussing some questions from JEE mains only. This is a question from 2024, and now you will see that whatever theory we have discussed, now the question will be a piece of cake for you. So the first question says, it is a statement based question. Statement 1 is, bromination of phenol in solvent with low polarity solvent like chloroform or CS2 requires Lewis acid catalyst. Now if we do bromination of phenol, sir, we very well know, because phenol is a very high activating group, so we do not need any Lewis acid. So the statement is saying bromination of phenol in solvent of low polarity like this requires a Lewis acid. No sir, in fact if we use polar solvent, do not use Lewis acid. Even though you use polar solvent, high bromination will take place, because phenol is such activating group. And even if you use non-polar solvent, still bromination will take place. But yes, because we are using non-polar solvent, but still Br2 will be breaking as Br plus and Br minus, and still Br plus will be getting substituted as electrophile, but to a limited extent. So mono-substituted product will take place. Anyway, we do not use any Lewis acid. We do not require any Lewis acid because phenol is itself supercharging the ring to such an extent that no use of Lewis acid is required. So it is saying it requires, so this is definitely false. Now, statement 2 says the Lewis acid catalyst polarizes the bromine to get, yes. Generally, if rather we would not had phenol, so the ring is not very much activated, so why Br2 will break itself? So generally for bromination we use Lewis acid like FeBr3 to do what? To force the Br2 to be get broken into Br plus and Br minus. So statement 2 is correct for general bromination. Statement 2 is saying Lewis acid polarizes. Yes, Lewis acid does that, but with phenol it is not required. So statement 2 is not incorrect. During bromination we require Lewis acid. So statement 2 is correct, but statement 1 is false. A very beautiful question which is actually asking that whether you know the theory from logical side or not. So answer would be statement 1 is false and 2 is true. Okay, so that means answer should be option D. Let us check. Yes, definitely correct. Now these questions you should definitely attempt by yourself also while practicing. Moving to the next question. So here assertion says aryl halides cannot be prepared. That means you cannot form aryl halide. That means I have an aryl halide and this cannot be formed by replacement of hydroxyl group of phenol by halogen atom. As in, if I have this phenol over here, then I have no arrangement of replacing this OH by halogen. Yes sir, we have seen that all the reactions of alcohol are not given by phenol, because in phenol we have this partial double bond character, because of which this bond cannot break, and therefore you do not have any process to form phenol from this to form that aryl halide from this phenol. Although we know the opposite process is possible, although that is also not easy, but through Dow's process we have some industrial application of a temperature pressure so that an aryl halide can be forced to become a phenol, but we have seen no reaction in which a phenol is changing into aryl halide. That means statement the assertion is definitely true. And let us I mean, what is the reasons? It is saying phenol react with halogen acids violently. Sir, it is contradiction. Alcohol react with HX. Phenol do not even react with HX. So this it is saying it reacts violently. So definitely it is false. So what is the assertion is right, but its explanation is because of the partial double bond character. The bond is so strong and X minus has no capacity to break that resonance stabilized partial double bond character. That is the exact reason. So assertion is correct, but reason is different, and whatever they have said, the reason is not even correct, because alcohol react with HX violently. Phenol do not even react with HX. So assertion is true and reason is false, as in assertion is true and reason is false. So option C will be your correct answer. Moving to the next question. The next question says phenol treated with chloroform. Now these are some exact questions which are if you know the theory, you will just tick the question and move forward. Phenol treated with chloroform in presence of sodium hydroxide is further hydrolyzed in presence of acid, results in, sir, this is the classic case of Remerteman reaction. So, but Remerteman reaction forms salicylaldehyde. Kolbe reaction forms salicylic acid. So, I do not have salicylaldehyde, but its IUPAC name is given. Its IUPAC name is 2-hydroxybenzaldehydes. Option D will be your right answer. You do not have to move your pen for such questions. Next question is, phenol, if you react phenol with zinc, so reduction takes place. So what do you form? Benzene. That means A is 3. So A is 3. A is 3. Two options are gone. Phenol, sir, this is classic Remerteman reaction. So it will form salicylaldehyde, as in B is 1. So again, just by checking these two, we know the answer, but we are practicing. So this is Kolbe reaction. So it will form salicylic acid. Phenol with concentrated HNO3 will definitely give you picric acid. So these are just NCERT reactions. Now this is also a JEE mains questions. So in JEE mains, whatever slides we have read, this proves that they are not important. They are very, very important. Moving to the next question. Again, now statement based questions are loved by JEE, as you can see through the proof. Statement 1 says picric acid is 2,4,6 trinitro. Sir, if it would be phenol, it is correct, but it is saying toluene, so it is incorrect. So statement true is false. Phenol 2,4 disulfuric acid is treated with concentrated HNO3 to get picric acid. Now we have seen that alternate path, although it's not there in NCERT, but still see, JEE loves it because that was an industrial fact we have discussed in the reactions of SE reactions of phenol. So yes, phenol treated with oleum forms 2,4-disulfuric acid, and when this is treated with a concentrated HNO3, because sulfur is a very good leaving group, so you get a good percentage of picric acid. So this is true. So one is false and one is incorrect and second is correct. That means option A will be your right answer. Moving forward, this is a classic. Now again, I mean, again and again you are getting the same thing. Now Remertiman reaction, it is asking about the intermediate. So let us see who will be the intermediate. No sir, it is not even reacting. Yes, it is an intermediate, but it should be O minus and Na plus, because post acidification we get this. And obviously that option we can see in Delhi. I know this Cl will also be further replaced by OH and then you get an aldehyde, but this is the most probable, because if I'm talking of the intermediate will be landing over here, because post after, I mean, this is also, but this is more or less after acidification you clearly get the product. So what intermediate would be the most probable intermediate of Remert? If I'm saying Remertiman, that means they are asking about the reaction of this gets added when chloroform is treated. So chloroform creates what? Chloroform creates dichlorocarbene. So dichlorocarbene, when attacks the substituted benzene ring, the ortho isomer is produced. This Cl getting replaced by OH is an example of SN1 mechanism. The Remertiman reaction acting species is this. So this should be reported as your answer. Now this is a good question, so let me check the answer also. Yes, it is option D. So if the question is asking you phenol converted to salicylic salicylaldehyde through intermediate, so the intermediate for Remertiman reaction will be when dichlorocarbene makes SE reaction at ortho position. So this should be your correct answer. Very important and a very logical question, I would rather say. Now the next question says you have to tell the reagent X and Y. Okay, so let us check what should be X. Here alcohol, the acid is remaining as acid, but this alcohol is forming an ester. So alcohol reacts with acid or its derivative. So X should be acid or its derivative. So this is acid anhydride, so can be correct. Acid anhydride, so can be correct. No, alcohol can't react with alcohol. And what is Y? This alcohol is remaining as it is, but this carboxylic acid now is turning into ester. So in order to convert carboxylic acid to ester, again you need to do esterification, but this Y should be an alcohol. So Y should be some alcohol. So out of A and B, what is alcohol? This is not alcohol, so option A will be your correct answer. Just you know the basic through NCERT and then you can make a JEE mains question. Moving to the next question. The next question says chlorobenzene, NaOH, this is high temperature and high pressure. We know, sir, this is Dow's process basic. So what you get is sodium phenoxide, because medium is still basic. Post acidification you get phenol, so we have got Y. And post concent, phenol is a highly activating group, so concentrated HNO3 will form picric acid. Just the similar question. So picric acid as an option C will be your right answer. Yes, definitely correct. Now moving to the next question. The next question says consider the given reaction sequence, sum of oxygen atoms in product A and B. So let us form these product A and product B. Alcohol when react with concentrated sulfuric acid, sir, we know this is oleum. So oleum forms what? Sir, oleum, although alcohol is a activating group, but because sulfonic acid group is large enough, so we get 2,4 substituted product. Remember, that was again there a JEE mains question. So this is just a similar question. And concentrated HNO3 will do what? Sir, it will form picric acid in a much better quantity. What is picric acid? Now, because nitrogen is a second period element, so it will be heavily substituted. And here you have to tell the number of oxygen atoms, the summation of oxygen atom. So this is 1, 3 plus 1 is 4, 4 plus 3 is 7, 7 plus 2 is 9, 9 plus 1 is 10, and 10 plus 4 is 14. So your answer should be 14. Let us check. Yes, 14 is your right answer. So a simple question, but yet checking your knowledge for NCERT. Now moving to the preparation of ethers. So after studying the reactions of alcohol, now this preparation of alcohol is very easy for us. Why? Because basically there are just two methods of preparation of preparation of ethers are very easy, because basically there are just two methods of preparation. First is by dehydration of alcohols, and second is by Williamson synthesis. Now the problem and the drawback, the limitation of dehydration of alcohols to form ether is you can only form symmetrical ethers. Now for sir, we have seen that dehydration of alcohol can produce alkene. We have done in the reactions of alcohol. Now we very well know, if we have an alcohol and let's say we use the famous dehydrating agent, which is concentrated sulfuric acid, which do what? Which gives H plus. So once it gives H plus, this oxygen gets protonated, and once it gets protonated, it can easily form carbocation. But we definitely know, sir, 3-degree carbocation is very stable. 2 degree is also stable. 1 degree, I have been repeating this statement over and over again. 1 degree carbocation is not stable. It is actually unstable. So practically, if I have a 1 degree alcohol and then but still with 1 degree alcohol, we have seen in alcohol, sir, but you said if carbocation is not formed, then E2 elimination can take place. So alcohol, when heated, but now I'm giving you the industrial value, the experimental value of the temperature also, heated till what? To 170 degrees Celsius, then you definitely get what you know, which is an alkene, because this high temperature around 170 degrees Celsius will be supplying this sufficient amount of energy which can further break this C bond H, because if you want to form an alkene, this C bond H should also be get broken, and in order to break this C bond H and introduce the electron of hydrogen to make it a pi cloud, extra energy is required, which is supported by this high temperature. But if the temperature is reduced, now it's an experimental fact of NCERT, you should remember it. So with concentrated sulfuric acid, if I reduce the temperature to 140 degrees Celsius, so around 140 degrees Celsius, what takes place? I am not denying to the fact that first protonation will take place. This protonated alcohol, now because this is a 1 degree carbocation, so it is not in a hurry of getting formed. So rather, if the temperature is also reduced, so this extra C bond H, the amount of energy required is also not sufficient enough, because we have further reduced the temperature also. So during such condition, what can happen is another alcohol molecule is still having the lone pair of electrons on oxygen, which will make it an electron rich species, so it can act as a nucleophile, and it can do a SN2 mechanism, which is backside attack, where this water will be leaving as leaving group and the oxygen of another alcohol molecule will be getting substituted. But sir, because this oxygen will give electrons, so this will attain a positive charge. Yes, so now deprotonation will result in the formation of an ether, but because the similar alcohol is also acting as a nucleophile, so all the time through this method, what type of ether you will get? It will have the similar alkyl group on both the sides, so it will be a symmetrical ether. But remember, because I'm explaining this through mechanism, so we can definitely say that this SN2 backside attack is only possible in case of 1 degree alcohol. And if I have a 2 degree or rather a 3 degree alcohol, then carbocation will not mind to be getting formed. So what will be taking place in that case? Even you reduce the temperature 140 degrees Celsius, then definitely elimination dominates. So this is a very, very, very important mechanism, obviously included by NCERT also. So I have written it separately, that With 2 degree and 3 degree alcohol, even if you reduce temperature, but still what will be the major product? Alkene. For example, this is a 2 degree alcohol treated with concentrated sulfuric acid. Temperature is also less. It is not 170, it is 140. So what we expect? Ether. But still now ether will be the minor product. How will get the ether? Obviously this H plus will protonate this oxygen. I will be getting this OH2 plus. Now, what is the first possibility of getting an ether? Another alcohol molecule of the similar type, like this one. It can attack. This can leave as a leaving group. So what you will be getting as a product? This is, I'm sorry, this is C. So let me remove this C. Now, another alcohol molecule is getting added. So this is alcohol. After deprotonation, this O will be getting added to this C. So this is also a symmetrical ether which you can obtain only when you have a 1 degree alcohol, because you can definitely see now this is also 2 degree alcohol, so the backside attack will be hindered. So whatever ether you were expecting, it will again be the minor product. And although the temperature is less, but this carbocation, this water, if let's say this water is gone, because the carbocation formed is quite stable, it is a 2 degree carbocation, and with this 2 degree carbocation, even at this lesser temperature of 140 degrees Celsius, but still there is temperature. So because this carbocation is stable enough, it will be formed. It will take time, and after the passage of time, because of heat, deprotonation will take place, and alkene will be your major product. Now, this is what you should know as per NCERT. But there is one important, one more, not important, but yes, obviously for good questions you should know this. Sir, what if we reduce the temperature to a more extent? If we reduce the temperature and bring it around 110 degrees Celsius, then in fact acid-base reaction takes place. As in, concentrated sulfuric acid at the end of the day is an acid also. It is a strong acid. So if it can give H plus, then it can force alcohol also to give OH minus. So this OH minus and the H plus of sulfuric acid will undergo dehydration, sir. Water is ultimately getting formed, and what product, sir? Acid base neutralization will create a salt. So what you will be getting as your product? The bisulfate, the alkyl, as an ethyl bisulfate should be your product, and water will be released. But this acid base neutralization takes place at even a lesser temperature, and experimentally that value is around 110 degrees Celsius. A very not very famous point for general questions. For good questions you should know this also, because now temperatures will also playing a part. So I'm summarizing it for you. At 170 degrees Celsius alkene will be formed. At 140 degrees Celsius ether will be formed, but only with 1 degree alcohol. With 2 degree and 3 degree alcohol, even if you use concentrated sulfuric acid at a lesser temperature of 140 degrees Celsius, still alkene will be reported as the major product, not ether. And the disadvantage of this process for ether formation is you can only prepare symmetrical ether. So sir, what if we want to prepare unsymmetrical ether? So in order to prepare unsymmetrical ether, we do Williamson synthesis. What is it? During Williamson synthesis, we need an alkyl halide and probably a 1 degree alkyl halide, because the mechanism here also is simply SN2. So for a backside attack of alkyl halide, I need a least substituted alkyl halide, and I'm using alcoholic or sodium phenoxide. So alcoholic in alcoholic medium, if I have a base, sir, but this alcoholic KOH, alcoholic NaOH, this is a reagent for elimination. That is why I'm saying here also, if you use 2 degree or 3 degree alkyl halide, this can also act as a base. So E2 elimination of this alkyl halide will take place. So if you want that E2 elimination should not take place, then you should precisely use only 1 degree alkyl halide, and base you can use whatever you wish to. and this will do an SN2. So sir, what is SN2? This can act as a nucleophile also. So this nucleophile will be attacking this R, X will be gone as X minus, and you will be getting your unsymmetrical ether. For example, let's say I have sodium tertiary butoxide. Now the base is very bulky. What is sodium tertiary butoxide? Let us draw it. Tertiary as in 3-degree carbon, butoxide as in O minus, sodium as in Na plus. Let's leave because this is a nucleophile we are interested in. And the alkyl halide we are having is the best possible. Why I'm saying best possible? Because this is not even 1 degree. Methyl has no least steric hindrance. It only has chotu hydrogen around it. So it is the best possible case for a nucleophile to attack. Now this nucleophile will make the attack and SN reaction will take place. So what we are getting, 4 carbons on this side with this O, and here you get CH3. So this is an unsymmetrical ether, methyl tertiary butyl ether. Again, sir, if I want to form aromatic ether, then can we do it? Yes, definitely. With this you can do it. How, sir? Let's say you have a phenol. First make it a nucleophile. So phenol with base, phenol is a stronger acid than water, so it can undergo neutralization. So what will be the salt? Your sodium phenoxide. So ultimately I have the nucleophile phenoxide ion. Now I am having the best possible alkyl halide. So easily this SN reaction will take place and you will form your aromatic ether. So this is methyl phenyl ether, commonly and famously, a very famous name of this aromatic compound is Anisole. I hope we remember this. So this is Anisole. Now rather, sir, if I'm having sodium methoxide, now methoxide as in this is quite, least hindered. But still this is a base. But now the alkyl halide that is given to us is tertiary butyl. So this tertiary butyl group has gone with a halogen. Sir, so this is an alkyl halide, but now SN reaction cannot take place because SN2 needs a very least hindered carbon. Because it is hindered, so this now can act as initially it was acting as a nucleophile, but it can act as a base also, because at the end of the day it just want to give electron. So because reaching this carbon is quite difficult, so rather it will give electron to this hydrogen, and what is getting from the elimination side, what are you seeing? So this is classic E2 mechanism. So this E2 mechanism will give rise to an alkene rather than a ether. So for Williamson synthesis also, you should keep in your mind that you should only get 1 degree, take 1 degree alkyl halide, because with 2 degree or 3 degree alkyl halide, again ether will not be produced. In fact, alkene becomes the major product. So these are the places where JEE loves to trick you. So this finishes our preparation of ethers, both symmetrical and unsymmetrical ether. Now coming to the reactions of ether, it is very easy. Why? Because practically speaking, ether is O with 2 alkyl groups on both sides. Oxygen being electronegative is getting plus I from this side also and this side also. So ether, just like alkanes, are normally not reactive. Ethers are stable to almost normal conditions. But if you are after them, पीछे ही पड़ जाओगे. For example, how can you make an oxygen atom angry? By protonation. So under vigorous condition, some reactions of ether are known. So because some reactions are known, so it is easy for us. So let us finish this easier thing. So that is what I have written, that generally they are inert, just like alkanes. But if you chirafy them, if you make them angry, how ether can become angry? When you protonate oxygen. So how to do it? Use halo acid, because mineral acids are strong acids. So HX are mineral acids, and using mineral acid is nothing but creating a drastic condition for ether. So if this ether is subjected to HX, so first what will be taking place? Let me go to the mechanism also, because mechanism is also common sense. So the lone pair of electron of ether under the influence of H plus will get protonated, and now the oxygen is angry. And now because the oxygen is angry, so it will try to snatch electron from any of the alkyl group. So if any alkyl group is willing to give electron, that means if the if after giving electron a stable carbocation is getting formed, then what will be happening? SN1 will be happening, reaction will be taking place. But how? With through SN1 mechanism. Sir, if at all no one is interested in getting that carbocation, as in no stable carbocation is getting formed, then rather the nucleophile, what is the nucleophile? Sir, we are using HX. So H plus has done its job. So now X minus will come, which will act as a nucleophile. So in that case, SN2 will take place. Ultimately, ether is going to react. But through what mechanism? SN1 or SN2 will decide that which alkyl group gets alcohol and which alkyl group gets alkyl halide. At end of the day, if HX is getting reacted with ether, it's a drastic condition for ether because ether is getting protonated. So one alkyl group will form alcohol and the other will form obviously alkyl halide. Sir, if we use this HX in excess, then we definitely know this is definitely formed. But this is an aliphatic alcohol, and we know through this alcohol, even aliphatic alcohol can get protonated. And after getting protonated, they will be substituted by X. So this alcohol will also convert into HX. But when? But when HX is in excess. So ether reacts tremendously with HX, can form alcohol and alkyl halide if HX is limited. But if HX is in excess, then you do not have to worry because water will be released. Oxygen of ether will be going in form of water and both the halogen will be taking the alkyl group. So it will be quite easy to predict the product if HX is in excess. Now, but sir, if we have aromatic ether, then we definitely know ultimately this oxygen is also going to get protonated, and now this bond is not going to break because again, like phenol, the lone pair of oxygen are again involved in resonance, so it will have a partial double bond character, and the double bond character is due to resonance stabilization, so bond will not break, just like the bond of phenol. So even if you use HX normally or HX in axis, this C bond O of aromatic carbon bonded oxygen will not break. So now only this CH3 is going to be broken. So post protonation, this oxygen will keep the hydrogen. That means you will get phenol in both the cases. This phenol is not going to react with HX, even HX is in excess. So in such condition, you will report phenol as one of the product and this methyl or any alkyl group with halogen as the alkyl halide. A very important reaction which you will see in the number of your JEE questions and even for your boards. Now, going to the last reaction of ether. The last reaction of ether is again the last and simple reaction of phenols, because now we are talking of aromatic ethers. As I've already told you, like OH, OR is also plus R group, but yes, I'm giving you an experimental fact that OR is a mild activating group, not much activating. It OH applies very strong plus R. OR applies plus R, but to a moderate level. Moderate level as in you can see that through the reactions that, sir, this is anisole. We definitely know this oxygen is a plus R group, so it will create electron density where at ortho and para position. But now this is not as reactive as OH. So if I take bromine in a polar solvent, how I'm creating the polar solvent? These are the direct NCERT examples I'm taking. So Br2 in polar solvent, if Br2 in polar solvent was taken with phenol, excessive bromination take place. We get 2,4,6 tri-bromo derivative. But here we are getting monosubstituted product, which is showing that here also we do not require Lewis acid. Here also we do not require any Lewis acid, which is showing that OR is also sufficiently activating the group. But Br2 even in polar solvent is not doing excess bromination. That means the plus R effect of ether OR group is much lesser than that of OH group. So monobromination will take place, and here there is no intramolecular hydrogen bonding effect. So again, para becomes your major product and ortho becomes your minor product, because ortho will be having steric hindrance, the bheed bhar. So because of steric hindrance, in cases of ether, there will be para isomer will become the major product. Similarly, if I do Friedel-Crafts alkylation, so this is anhydrous AlCl3. This is the alkyl chloride, so CH3Cl. So orthopara, so para isomer will be your major product, ortho will be minor. If we do Friedel-Crafts acylation, you can do that also. So we are doing it with acid chloride of acetic acid. So this is ethanoyl chloride. So this acetyl group will be going at ortho and para position, and para will be a major product. Now we definitely know benzene ring with COCH3 is generally known as acetophenone. So this acetophenone is substituted by methoxy group at the para position. So this becomes 4 or para methoxy acetophenone, the major product. Now IUPAC, although acetophenone is a general name, but for organic compound, even general name are considered as IUPAC name, hence discussing names also, and these are direct NCERT examples, very, very, very famous. Now, last, nitration, what reagent? Concentrated HNO3 and H2SO4. Here I'm using H2SO4. In phenol, we have just taken HNO3. Even taking HNO3 dilute would be doing the job, mononitration. Here, with HNO3, I'm using H2SO4 also. And by doing that also, still we are getting product, but mono substituted, which is showing, again I'm telling you, OR applies plus R, optimum amount of plus R, it has a strong plus R, but not that strong as like that of OH group. So it is also plus R. So ortho and para directing, where para becomes a major product because para is having no steric hindrance. No steric hindrance as compared to ortho, para is having minimum steric hindrance. So these are the reactions of ether. Now directly moving to some practice questions so that we can wind up this chapter of alcohols also. Now the first question says, let us read the question. What is the suitable reaction condition for preparation of, we have to form an ether, phenyl this side, methyl this side. So this we have to form. So again, we can do it through Williamson synthesis. Now this minus can go to here. Yes. So this can definitely form. So the question is, so obviously this will be answer, but let us check. This minus can, no. So this is not alkyl halide. Who is a better leaving group? C bond X. This is C bond O. C bond O cannot be broken, so this can't produce. Now phenoxide is available, methyl is available, so this can also form. So phenoxide will come, and okay, so let us check. Okay, that first cannot take place. Why? Because this is phenyl, so this is aryl halide. Aryl halide, again in aryl halide also there will be partial double bond character. So aryl halide do not react simply with like alkyl halide. So this will not take place. So rather C is better. Let us check D also. Benzene, obviously there benzene can't react with alkyl halide, so this is obviously not possible. So option C is our right answer. Let us check. Yes, definitely correct. Moving to the next question. The next question is an assertion reason. Assertion says synthesis of, okay, I'm sorry, it says synthesis of ethyl phenyl ether. Ethyl phenyl ether, as in one side we are having phenyl, one side having ethyl, can be achieved by Williamson synthesis. Yes, because that is the purpose. We have read Williamson synthesis in order to prepare unsymmetrical ethers. So this is definitely true. Reaction of bromobenzene with sodium ethoxide, so ETO minus and Na plus, yields. No sir, again the similar question it is asked. So these all are JEE question. This is JEE 2024. That was also a JEE mains question. So sir, this is again the similar logic. Aryl halide cannot react, sir, but it is saying this can form. No sir, this is wrong. So that is true and this is false. So first is true and second is not correct. So option B will be your right answer. Let us check. Yes, definitely correct. Moving to the next question. The next question says major product of the following reaction. Now sir, this is an alcohol. Alcohol is reacting with a base. Sir, base and alcohol can do what? It can form salt. Although this is a substituted phenol, so what? Now sir, now this is the nucleophile. So these questions are very easy for us now. And this nucleophile is going to react with CH3I. So this is classic SN2 mechanism. So this CH3 will remain as it is and it will be substituted by CH3. So this will be any sol substituted with CH3 at the ortho position. So any sol, no any sol, any sol, yes. So B is your right answer. Let us check. Yes, definitely correct. Moving to the next question. Next question says, which one of the following reaction is not possible? Okay. So ether with HBr, yes, this can undergo protonation. So here H will be getting formed, but we definitely know this is a partial double bond character. So this bond will not be broken. So this Br minus will be going to this CH3. So there will be formation of CH3Br and definitely this phenol. So this is feasible. And because it is feasible and in the question we are asked which is not possible. So because this is possible, so not an answer. Talking about this one, phenol, yes, it can get protonate, but after protonation, sir, after protonation, this C mondo cannot be broken because it is resonance stabilized, because it is forming. So this is okay. So this is not possible. So this is not possible, hence an answer for us. But because we are practicing, so let us check other options also. Chlorobenzene with NaOH, high temperature, high pressure. So this is just the concept of Dow's process. So yes, it is also possible. This, sir, this is Cl2 in presence of anhydrous AlCl3. So it will create an electrophile Cl plus. Because we know it is a plus R group, so it will be ortho and para directing, where para will be the major product. So para becoming major product. So this is also possible. So our answer will be option Bombay, definitely correct. Moving to the next question. The next question says, major product. Now we have to pick the major product from the following reaction sequence A and B, and we have to tell the sum of pi electrons in product A and product B. So let us form these product A and product B. So let us form first A. This reacts with Br2. So when it undergoes reaction with Br2, the pi will be getting vicinal dihalide, because alkene with Br2 forms vicinal dihalides. Now this vicinal dihalide is getting reacted with this O minus. Okay, it is having alkyne also, but alkyne does not react with alkylide. We definitely know this is a nucleophile, and because it is saying it is one equivalent, so only one alkylide which will react, any can react, it will form the same product. So this minus will be doing the substitution, and the product that we will be getting is, after this bromine, let us count the number of carbon. So this is the oxygen having 1, 2, 3 carbons. So 1, 2, 3 carbon, and this is having a pi bond. So how many pi? Now in the question it is saying the total number of, not pi bonds, pi electrons. So this is 1, 2, 3, 4. So I have 4 pi electrons over here, but this is in product A. We again have to calculate this in product B. So let us see product B. This is again reacted with Br2, so this is definitely going to be formed over there also. But now this is reacted with alcoholic KOH3 equivalent. So what does alcoholic KOH do with alkylides? Are elimination. So this bromine, if this hydrogen is gone, I'll get a pi over here. If this hydrogen is gone, I'll get a pi. So beta elimination happening 2 times. Why I'm making these 2 pi bonds? Because then they will be conjugated pi, and when you, through beta elimination, whenever you are forming a product, what alkene you produce, you always produce a more stable alkene, and which is more stable, stabilization effects. A resonance conjugated alkene is resonance stabilized. So ultimately what will be your answer? Sir, when these two guys will be gone, pi bond will be coming here. When these will be gone, pi bond will be, sir, but here we only require 2 equivalent of alcoholic KOH. Question is giving you 3. So with 1 KOH, it will not react. If you are supplying me some reagent, I even have an option of not reacting, right? So it definitely will require alcoholic KOH, but 2 equivalent. So 1 will be giving no reaction. So ultimately this will be your product. This is how JEE, this is a good question. This is how it is. They are confusing you. So now how many pi bonds? I have 2. So how many pi electrons? So here also we have 4 pi electrons. So total 4, 4. Total number of pi electrons. Electrons are 8. So total number of pi electrons are 8. Yes, answer is also 8. Now let us try this question. I hope you can attempt this. So I hope you got the answer. Now this is also very classic and common case where protonation of this ether first will take place. Now you tell me, sir, this will be a very stable carbocation. So once after protonation, this will take electrons, so this will be a very stable carbocation, a tertiary butyl carbocation stabilized by 9 hyperconjugating hydrogens. So this carbocation will be definitely very much willing to be formed, and this stable carbocation will then take the X minus, so this will be your alkyl halide and that will be your alcohol. So that is the alcohol, that is the alcohol, but that should be your alkyl halide. So option D will be your answer. Now let us attempt this question. So I hope you solved it, but these are some questions which definitely make you question the fact that whether you are learning by mugging things up or whether you are actually participating in the common sense that even NCERT gives you. Now, why I am saying this is because I have just made the structure properly. And by looking at the options also, you can see in all the options that something cyclization has to take place. So what common sense we can apply, not from rocket science, from NCERT, from whatever we have studied. Sir, we have catalytic amount of H2SO4 that will give H plus. H plus, first we have to think about H plus only. H plus do what? Sir, H plus protonates. So who has the capacity to getting the protonation? Sir, the most polar bond we know, carbonyl is a very polar bond. We have seen in the mechanism of esterification also. Although with esterification we formed ester, and here we already have an ester, but since this is also a beginning for the next chapter of R, which is carbonyl compounds, and because we know in esterification also we have taken the carboxylic acid, and who has got protonated in the beginning, sir? The carbonyl oxygen, because this carbonyl group is highly polar. So once it gets protonated, it attains a positive charge, and whenever oxygen attains a positive charge, it gets angry and it will demand electron from the carbonyl carbon. So ultimately this guy will get the positivity. Now once this guy has got the positivity, and with options also we can see, with ether also we have seen that whenever a carbon was having positivity, even an alcohol can act as a nucleophile. So if this alcohol act as a nucleophile, it will give electron to this carbon. Now once electron is given by this oxygen, that will gain positivity, so it will snatch that electron from this. So ultimately what you are going to have, sir, okay, one more thing, because we have an ethyl group also over here. So I am just giving you, I'm modifying the common sense that once, just you need to understand that once this has been protonated, once it is protonated, it will get a positive charge, and this positivity, yes, I'm not denying to the fact that this will be attacked by this oxygen, but this oxygen can even make this OET, the OR group, the O ethyl group, as a leaving group. So once, because if this gets eliminated, what product you can see? Sir, this is a phenol, agreed. Sir, this is a CH2. This is again a CH2. It is connected with an O. That O, after giving electron, gains a positive charge, so it will neutralize itself by taking and snatching electron from that hydrogen. And this will be attached to this carbonyl group with a double bonded O that is connected with the benzene ring. Now that what I have done initially is I have made this pi bond as a single bond. Although that is the first step that is going to happen, but when that pi bond attains, it can also give back the electron and then OET. Actually that is the case of, but that you should only know for your advanced question also. But technically speaking, pi becomes sigma, and when oxygen again gives electron, ultimately this OET leave as a leaving group. So my point is, even with options, you are getting that help that in every option you have to think of cyclization. So here a cyclic ether is getting produced, and therefore I have taken this question in ethers. But ultimately this question should come when we will read carbonyl compounds, because then from after reading carbonyl compounds, such mechanism will be more doable, more practical, and more probable for us. But because over here what is getting formed, a cyclic ether, and I guess you can clearly see that cyclic ether in option A. So option A is our right answer, and a very good question which is also opening the gate and asking a requirement. Yes sir, we need to understand something about the carbonyl group also, which will be our next chapter. So let us finish and conclude this last chapter. I mean this chapter of alcohol phenol ether, the last topic, the last few questions. The next question says, I have an ether and an alkene and I have concentrated HBr, but this concentrated HX is an excess. So what it will do? First protonation. So this first ether will get protonated. I know this bond will not break. So ultimately this will be gone with Br minus. So ethyl bromide and phenol. Ethyl bromide is not there in any option. So this phenol is definitely correct. This is wrong. This is wrong. This phenol is definitely correct. Now sir, what about alkene? Sir, alkene also react with HX. So when H plus attacks, when this is attacked by H plus, you will get a carbocation. Where carbocation will be stable? Sir, benzylic carbocation. So that benzylyl group is going to get the nucleophile, which is Br minus. So where I'm having Br over there, here, acha, okay, on in here Br is over here it is there. So this is wrong. Option D. I mean, now this is just a question of alkyl halide. Moving to the next question. The next question is also, although it is appearing difficult, but if you just decode this question with common sense, you will give your answer. It is also a JEE mains question. Now this is an ether. Sir, again HXC. Similar question are getting asked. So after protonation it will form H plus. This will be 1 degree, this will be 1 degree. So sir, 1 degree is not formed, so SN1 will not take place. Then what? I minus. If I minus is attacking, question is saying it will form A as alcohol. So where I minus will attack to the least hindered carbon. Which is least hindered? This is also 1 degree, this is also 1 degree, but over there the hindrance is larger, because although not at alpha position but at beta position it is hindered. So for SN2 this should be the best possible case. So I minus will be going to this carbon and bond will be breaking like this. So that will be your alcohol. So your alcohol will be 1 carbon, 2 carbon, 3 carbon, a methyl branch, this C and OH. So this will be your product A. I hope we are clear till this. After that, so then H2SO4 and heat, that is reagent for what? That is reagent for dehydration. So after that, dehydration will take place. So it will be attacked by H plus. This OH will be gone in presence of water. And once it is gone, I get a carbocation. 1 carbon, 2nd carbon, 3rd, 4th. Because I'm getting a carbocation over here, so obviously I can see there will be hydride shifting. So plus will be coming over here. So this is the positivity. Now what are the beta carbons? This one, this one, this one. But if I get a beta elimination of this carbon, then I will be getting a more substituted, more stable alkene. Hence hydrogen of this beta carbon will be taken, and the most substituted product will be this one. So this should be your alkene, and this alkene is given, I guess, in option number C. So such questions. Now see, for alcohol question you should also learn the basics of GOC, alkyl halide. So that's what I'm telling you, that organic chemistry generally is a packet. Yes, you get some straightforward questions also, like we have seen in the previous slides. Simply Remer-Timmerman reactions, so naming reactions you should know. And if else mains is supplying you question, it will supply you question which will be a mixed packet. So you should know organic as a common sense. Now again, an example of this fact that organic is a common sense. Now 1 methylene oxide. So one extra information, for advanced such questions are very famous, but for mains they are rare. But still I have taken some questions of ether which will require us to move a bit one step ahead. So not actually ahead, you just need to know what is ethylene oxide. It's a cyclic ether. The general name of ethylene oxide. This is the compound called ethylene oxide. It's a cyclic ether. Cyclic ether containing eth as in 2 carbon, lene as in at vicinal position. I have oxide as in O. Now at first this is first carbon, this is second carbon. Any carbon can become first carbon. So in the one carbon you are having a methyl group. So this is C. So this is our reactant which you should know. So told you. Now when it is treated with excess of HBr, so excess of HBr, so first let us react with HBr. So H plus will be protonating this oxygen. Now post protonation, you tell me what will be formed. Now B, after that Br minus. So cyclic ether we already know. So 3-membered ring is having a lot of Bayer strain. So I mean, yes, this oxygen will not have sp will not but ultimately its hybridization is also sp3. So the ring will try to open up. So where carbocation will be more stable. So for opening of cyclic ethers you should always think of stability of carbocation. So where carbocation will be more stable, so this will be a 2-degree carbocation. So after protonation, O will be going to this carbon and the nucleophile, which is Br in this case, will be coming to this carbon. So ultimately our product will be, this will be OH and this will be Br. But question is asking us excess of HBr. So remember, with ether we have HX limited or HX excess. So that is asked over here. So now if we react with another mole of H plus, then this alcohol will get protonated and ultimately you get Br minus here also. Now because it is excess of HBr, so it becomes an easy question. Else it would have been a good question. If this was asked, it would have been a good question. But because it is using excess, so remove both the oxygens. So ultimately, if I have 3 carbons, so this is 1, 2, 3 carbons. So 1, 2, 3. Yes. Option D is your right answer. Let us check. Yes, definitely correct. So I hope we are clear with till this. Moving to the next question now. This next question is also using some common sense, although you will again see this in the chapter of amines, but because we have already discussed mechanisms also, so let us do this with common sense now. This is an acid anhydride. So sir, with acid anhydride, what reactions we see? We have till date we have seen esterification. So if you remember the mechanism of esterification, then we very well know this carbonyl group. This carbonyl group used to get protonated. But do we have H plus? No, sir. Sir, this is happening in presence of pyridine, so protonation is not there. But yes, I'm not denying to the fact that you have to think of the mechanism of esterification. But we know this is a carbonyl carbon having positivity, and the lone pair electrons are minus. So minus plus attraction. But you tell me, if oxygen lone pair can attack and can go here and can do this replacement, then ester will be formed. This is how you will think of the esterification. But just ask yourself, if O lone pair can do this, then can't nitrogen lone pair can do the same? Yes. Because when O will do it, it will snatch electron from hydrogen and become neutral. Even nitrogen can snatch electron from its hydrogen and get neutral. That's what I'm saying. You have to think the logic of esterification, and this actually we will see in the chapter of amines also. But can't we see that organic is related through common sense? If oxygen can give lone pair, then nitrogen can also give lone pair, and through the chemical bonding and periodic table knowledge, we know oxygen is more electronegative. So the tendency of giving electron by nitrogen will definitely be relatively higher, is what I'm trying to say. So nitrogen giving electron and snatching electron from hydrogen, and this leaving group will be actually giving us the major product. So our major product will be this benzene ring will remain as it is. This is 1 carbon, second, third. The OH is as it is having a methyl group, and this nitrogen with an H, because one hydrogen is gone, because nitrogen after giving electron has snatched the electron of hydrogen, and it has been just introduced by this acetyl group, and this CH3COO with this H is left as acetic acid. So where do you see that product? I guess you can clearly see in option number D. Now this is a good question. I'm saying this is a good question, and we will see some question in the chapter of amines also. But why I have taken this chapter, this question over here, sir? Because this is question of carbonyl compound and amines. But I have taken deliberately in the chapter of alcohol because I want to tell you that things are related. So moving to the next question. Now these are some straightforward questions which you get in your JEE papers. This is also a JEE mains question. The question says, this is aromatic ether concentrated as in nitration. So nitration will bring NO2 at the para position. Ortho para becomes major. So this will be A. And Br2, now bromination, because it is NO2, so this is deactivating, so it will be meta directing. This OCH3 is activating, so it will be ortho and para directing. So these are the positions because para is occupied. Because it is saying excessive bromination, so bring bromine at both the places. You are asked A and B both, so A will be NO2. Ortho is not possible, para is possible, and excessive bromination will bring bromine to both the sides. Your answer will be option number B. Now moving to the next question. This is again a JEE mains question. The question says compound is heated with HI and you get A. So again the ether problem. So after protonation, sir, this will not be broken. So this will rather become phenol and I minus will be attacking this carbon. So this, okay, they are not asking this guy, because if they would have asked, then I would be there. So what will be A? The organic compound will be phenol. So A will be phenol, as in this. These are wrong. And phenol when treated with zinc, sir, this is classic case of reduction of phenol. So ether mixed with phenol. So after zinc in heating, oxygen will be removed in form of zinc oxide and you get your benzene. So option D, because this is benzene. So these are some clear questions which you can do through just NCERT. Now, again, a good question from JEE Mains 2022. Good as in logically good. So you are attacking H plus. So who are the candidates of receiving this H? If this lone pair of electron of ether will receive H, so, but why it will receive? Why I'm thinking of before doing this is, carbocation will not be formed over here, and this will be 1 degree carbocation. So ether Y will want to break. So think of another option. So that can go to this oxygen lone pair, can also be get protonated. But again, after deprotonation, I'll get only 1 degree carbocation. So rather, pi is also a very weak bond. So we obviously know that pi cloud also can attack H plus, and now if I get a carbocation over here, it will be a resonance stabilized carbocation. So this was the most trickiest part of the question, that where you will think of the protonation, and you can only do this once you read things logically. So this oxygen lone pair sigma plus will form this carbocation, and this carbocation is not weak, it is resonance stabilized. So this will be formed and carbocation is formed. Now once carbocation is formed, now alcohol will be ready with its lone pair, attacking this carbon and snatching electron from hydrogen. So again ether formation will take place. So this is also classical case of formation of ether, not practical, because practically we are having dehydration of alcohol and Williamson synthesis, but through common sense also we can form ether. So a ring with an oxygen, a ring with an oxygen, a ring with an oxygen, this is not possible, this is not possible, and this oxygen is connected with 1 2 3 4 carbon with one branch, 1 2 3 4 carbon with one branch. Okay. We do not have to count the number of carbon. We just have to see that stability of carbocation is over here. It is making so this is not stable carbocation. Therefore, this is wrong, and this was making a stable carbocation. So option D is your right answer. Let us check this. Yes, option D is your right answer. I hope we are clear till this. Now, this next question is again it is the same common sense, but repeating it for you. So after protonation, this will be a resonance stabilized bond, so it will become phenol. Substitution can't take place. This can be phenol, this can be phenol. Let us check for this one. This ether will also get protonated, but okay, now if this bond gets break, if this bond gets broken, so I get a positivity over here. If I get a positivity over here, you can clearly see this carbon is connected with a highly electron withdrawing group C triple bonded N. Triple bonded carbon is also electronegative, connected nitrogen. So this is a strong electron withdrawing group. So if I get a positivity over here, electron withdrawing group destabilizes carbocation. So carbocation is not going to be formed over here. Even delta positivity, even SN2 cannot, SN1 cannot take place because carbocation will be not stable, unstable. And SN2 cannot take place because this is quite hindered carbon. So no substitution can take place over here. And because no substitution can take place over here, so post protonation after H plus attacking this, there will be one only possible case, that bond will be breaking like this. So you will get an OH over here, and these carbon will be getting the I minus. This carbon will be getting your I minus. So it will be isopropyl iodide, and this benzylic carbon will have CN also and OH also. So this will have no substitution can take place over here. It will have CN and OH. A very, very, very good question. So I hope that, yes, I hope that was the last question. I mean, I know now that was the last question. So this is it from my side. All the very, 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 very best for your boards also, for your revision also. These lecture notes and the practice questions you can obviously download for free from the link. Just go to the link in the description section and go to PWAT app and download everything. Revise this if you want to, and we will meet soon with the next chapter of carbonyl compounds. Bye bye.